What you are seeing behind me is Dot Survivors, a complete game developed by me using Unity's data-oriented technology stack and their entity component system, and it's available right now for free on Steam. However, Dot Survivors is more than just a game. It's actually a massive learning resource to help you learn about creating a game using Unity, Dots, and ECS. Now, I'll talk about that a little bit more in just a bit, because that's actually not the topic of this 5-hour-long video. What I wanted to do with this video to kind of celebrate the launch of Dot Survivors is put up a simplified tutorial where I'm creating a Survivors type game to help you learn to create your first game with Unity, Dots, or ECS. So this tutorial video is going to focus on the technical implementation of creating an ECS-based project. If you want to learn a little bit more about the theoretical side of things, or if Dots and ECS is even right for you, I'll point you to another video that I created where I kind of go into more of the theoretical side about what exactly Dots is and if it makes sense to use it in your game. Now with this video, I wanted to go into a bunch of the very common concepts that you'll see in ECS-based projects, and hopefully by the end of this, you'll have enough knowledge and tools to create your own projects using Dots and ECS. Now, if you do want to take it a step further, I'll point you over to the Unity Asset Store where I just put up the project files of the shipped Steam game Dot Survivors for sale. So this includes all the source code developed by me, as well as all of the art and audio assets created by Sil and Emil of Penzilla Design. By the way, I think they both did a tremendous job on this project, and I'll leave some links to their website down below if you'd like to hire them or purchase any of their asset packs. Now, with this asset store product, I'm not just going to give you all the project files and let you figure everything out. I actually have a massive documentation site that includes documentation on a few dozen of the most important concepts of this game. And if reading through a bunch of documentation isn't really your thing, don't worry. I do have video overviews where I go over the code as well as any editor configurations for each of these concepts. And there's also a full API section of the documentation where you can get more information about each and every type. So pretty much I wanted to document everything in this game, so if there's anything in particular that you're interested in, you can learn about it. Anyways, I could talk about this asset store product all day long, so I'll just leave you some links down in the description below if you want to learn a little bit more about it. So let's get back to today's tutorial, this Survivors type game. Now, I do think that before going into this tutorial, it would be helpful to kind of understand some of the core concepts of data-oriented design. And again, I'll have some resources down in the description below where you can kind of familiarize yourself with these things, because if you don't, then you might kind of think that a lot of the things that are happening in this video are a little bit overcomplicated, or it's like, why would we do something this way when we can just do it in regular Unity some other way? So I think having some kind of the fundamental theoretical understanding of these data-oriented design concepts would be quite helpful for additional context. But certainly to follow along with this video, you will need to be fairly familiar with C# and Unity. Now I'll put the specific Unity version and ECS versions that I'm using up on screen right now, but the hope is that Unity doesn't change things so much that this tutorial should be relevant throughout the Unity 6 generation, as well as the Unity ECS 1.x. And if you'd like to, you can follow along with your own empty project. However, down in the description below, I also have some links to the starter and final project files. So if you want to start with the same project files as me, that's awesome. I do have some of the art assets from the Dot Survivors project included in that starter project. That's what we're going to be using to develop this project. And there's also a custom animation shader and some UI stuff, just kind of like regular game object prefabs that I don't want to spend time in the tutorial showing you how to create a little UI thing. So all that stuff is just saved within those project files. So anyways, without further ado, let's get into the tutorial. Okay, so just going to start things off with a quick little overview about what you need set up in your Unity project before following along with this tutorial. Now, if you download the starter project files that are available through the link in the description below, all this stuff should be set up for you, but still good knowledge to have if you want to create your own ECS project. So far you'll see that I've included some of the art assets. So I do actually have a font that we're using, as well as some materials all set up for the different alien, astronaut, background, some little boulder environment elements, the gem, the plasma blaster, and the Reaper alien. I do have a animated shader available as well, and I'll be going over kind of how this works and how I'm using this to actually create 2D animations in this project. Of course, I have all these sprites available for all the necessary art assets. As far as scenes go, I have just a title scene here that's set up with just the game logo as well as buttons to play and quit. And this has an attached UI controller already set up for it, so you don't need to worry about that. And then going into the moon level, we do have a couple things set up for just the Cinemachine camera, which will be kind of completing the setup of that when we get to that portion. I do also have this game UI, which does include a pause screen where you can resume or quit, because we will be implementing gameplay pausing. And we'll have a game over state as well. So this game over screen will display and prompt the user to quit back to the main menu. And then this game UI also does have its own game UI controller script on it. And so everything is kind of wired up. So all the kind of game over stuff and pause menu stuff is all functional. We're just going to have to kind of invoke it from some things on the ECS side, and we'll be getting to that kind of like towards the end of this tutorial. As far as scripts go, I just have the UI scripts. So here's the game UI and main menu UI controllers, and then I just have the Text Mesh Pro Essentials imported as well. So that's as far as asset goes. As far as the actual project setup, we can go up to Window and Package Manager, because there are a couple packages that are required. So most of these things are just imported by default when you create a new Unity project. However, I added 4 additional packages. So we have the Cinemachine package, because we're going to be doing some stuff with the camera following using Cinemachine. I also have the Entities package. Of course, this is an ECS tutorial, so we need the Entities package. Entities graphics package is also required because we're going to actually be rendering things on the ECS side. And then finally, the last package that we need is the Unity physics package. And this is the Unity dots physics package. And that's because, again, all of our collisions and everything like that is all happening on the dots and ECS side. I will point out that the Unity physics package, also, if you do go to the samples tab, there are these custom physics authoring components. And I typically use these, although Unity seems to be pushing people towards using just the regular Unity physics components to essentially author our dots physics components. So that's what I'm going to be showing in this tutorial today. But do just know that if you do want to experiment with the custom physics authoring components, they're just available through the samples tab on the Unity physics package in the package manager. And then as far as project settings go, there are a couple things that we need to set up. So if you just go to Edit and Project Settings, in the window here, we can go to the Editor section and scroll down towards the bottom, and there's these enter play mode settings. So this says when entering play mode, we'll make sure this is set to do not reload domain or scene. And this is just kind of the what they call the fast enter play mode options. So you'll see that when we actually get into testing our game, you know, after Unity is already compiled and everything like that, when we hit play, it just kind of immediately puts us right into the game, and we don't have to kind of wait around for domain reload, which is real nice. Now, there are some limitations for using this if you're using any type of static variables. These actually do not end up getting reset. However, we're not using any static variables in this project, so that is acceptable in this case. Then going down to the physics settings, we can see the layer collision matrix here. And I've added a couple of physics layers. And again, this is just kind of through the regular Unity layers workflow. And because we're using Unity's regular physics authoring components, this is actually how we manage kind of the different types of objects that can collide with each other and all that. So I've added different layers for player, enemy, player attack, environment, and gem. And so these are all the things that are essentially going to be available to us in our game. And you'll see that the layer collision matrix is very simple. You see that I've just kind of like disabled most of the options here. And then we have the player colliding with gem, environment, and enemy. And then the enemy just needs to collide with player attacks as well as other enemies. So a pretty simple collision matrix, and that's all we really need for the interactions that we're using in this little tutorial project. Okay, so I think that's enough little project overview. So let's get into actually creating some ECS things. So the first thing that we're going to do is inside this moon level, we're going to right click and go to new subscene an empty scene. And then here we'll be prompted to create an empty scene inside this moon level directory. So let's just go ahead and call this moon entity scene. And then here it'll open up a dialog box prompting us to create a new subscene inside this moon level directory. So let's go ahead and just create a moon entity scene here. And you see that this moon entity scene is now part of our regular scene hierarchy. Now the idea with subscenes is we can kind of add game objects to this subscene right here. And then during a process known as baking, these game objects will actually get converted over to ECS entities. The whole idea is that we take game objects and we have these things called authoring components on them. And these authoring components define how we take data that we are modifying inside the Unity editor and convert that over to ECS compatible data, some things that we've defined, some things that Unity has defined. There's also a ton of other advantages of subscenes. You know, we can have a bunch of these and be able to load these in and out, especially for larger worlds. This is a really nice feature to have. And it's really cool that we can just kind of like bake all this data inside of a subscene. So, you know, sometimes there may be some heavy calculations that you want to do ahead of time, and you can kind of like bake all that data into a subscene so that some expensive operations don't necessarily need to get ran on a endpoint machine. So let's start things off just by creating a very simple environment entity that we can have in our scene. So we'll just go to the moon entity scene here, right click, we'll go to game object, 3D object, and then we'll select quad. Now, the idea here is that we're actually going to be using quad meshes to render basically all the entities in our scene. And then we just have materials that are going to render on those quad meshes to, you know, display these sprites within our game. And also on those materials, we can have some custom shaders, and that's how we're going to be accomplishing animations. But, you know, we'll get to that in just a moment here. So anyways, we have this quad. We can just rename this to boulder. And then you see that we do have a quad mesh associated with it. And then for the materials, instead of this just regular material here, we can add the boulder material, which is one that is available in the starter assets. And then I'm actually going to remove this mesh collider and instead just use a regular box collider. Don't want to use box collider 2D. Unfortunately, we can't use the 2D colliders to author things in ECS just quite yet. And so we can kind of zoom in here and just kind of just slightly the collider edges so it's nicely wraps around the visuals of that there. And just real quick, gonna cut in here and say that I forgot to mention that when we're setting the size of these colliders, make sure we set the Z value to a value of 0.15 because by default, it's like a very small value and we want it to actually have some amount of thickness so these collisions can actually take place. And I'm actually also just gonna go ahead and increase the scale of this to be 1.75 just so they're a little bit larger in the game view there. So there we go. We have a nice little boulder here. And again, these are all just kind of regular Unity components at this point. So I will go ahead and enter play mode here. And you'll see that we still do have our boulder inside of this entity scene here. And so far, nothing has changed in the inspector. It looks all the exact same. Now, I should mention that the inspector kind of has two modes associated with it. So this is sort of the authoring mode, where we can use regular Unity components to author data on the ECS side. Now, by going to this little circle icon right here, we can change this over to be runtime. And runtime shows the actual ECS runtime data that is available to us in the editor. So you'll see that things are starting to look quite a bit different now. So we have kind of this local transform, which defines the position, rotation, and scale within its local space. So if it's, you know, part of any transform hierarchy, this is kind of the, you know, relative values to its parent. We also have the local to world, and the local to world basically defines the world space, position, rotation, scale of this object. Now this is listed as a matrix 4x4, and this is kind of used for more efficient rendering and things like that on the GPU. And, you know, we're typically not going to be modifying things on this local to world component directly. Unity actually has its own little process of it converting this local transform into a local to world. Kind of scrolling down, we have some other things related to render bounds, the entity's graphics, physics world index, render bounds, render filter settings, render mesh array, scene section, scene tag, world render bounds. Most of these things are just kind of all Unity built-in things that allow, the game to just kind of function as expected. However, as we go on and we start, creating characters and enemies and gems and things of that nature, we're going to start to create custom components, and we'll be able to inspect and edit these custom components from this inspector right here. So let's go ahead and just kind of populate this scene real quick with some of these boulders. So just go ahead and just duplicate a bunch of these, just kind of around the screen here, just so we have like, a couple little environment assets, some kind of points of reference for us, for the player, just kind of moving around within the game world here. And I think that should just be plenty for right now, but of course you can add more later if you'd like. So now let's actually get a player inside of our game world so we can have them, walk around in this environment here. So again, we'll go up to this moon entity scene, right click, we'll create a new 3D object, and we'll just go ahead and start with a quad here. And then we can name this player. So by the way, you will see that the inspector is showing invalid entity right now, and that's because we're still on the runtime mode. So we do need to swap back to the authoring mode when we're changing around components on here. So again, I'm just going to remove this mesh collider, and then we can go ahead and pop open the mesh renderer, swap out the mesh for the astronaut material, and I'm going to go ahead and increase the scale on this guy to 1.5, and I'm just going to zoom in here, and we should see our nice little astronaut in the game world here. When we get to the portion of character animations, I'm going to go over kind of like how the shader and animation works, but right now it's just kind of on one frame of animation, and it's just going to be stuck like this for now. Anyways, let me go ahead and add a box collider on this guy as well, and we'll go ahead and set this to match the graphics, so this kind of all lines up nicely here. Perfect. And also don't forget to set the size of the box collider on the z-axis to 0.15. And then another component that we are going to need on our player is a rigid body component, and this is because we want our character to interact with the physics simulation, so we're going to add a rigid body on here. For mass, let's go ahead and set this to a value of 100, and for linear damping and angular damping, we can just type in INF for infinity. The idea is that we're basically going to be in complete control over, how the character moves, and we don't want to apply any damping linearly or angularly. And then we can also just go ahead and uncheck the use gravity box here. And that is all that we need for now. We will be changing one other thing on here in just a second though. So let's actually get our player to move around in the game world. Okay, so in the scripts directory, we're just going to go ahead and right click, go to create scripting, and we'll just create a regular mono behavior script. And we're going to be using this to author some things about the player. So actually what we're going to do is we're going to create kind of a general character authoring. And the idea with this is this authoring component is actually going to be used by both our player characters as well as the enemy characters within the game. Okay, so we can just open up this character authoring right here and just clear out any of the template stuff if it opens up with that. And then, so what we're going to do is we're first going to deal with actually moving this character around our game world. So in order to move them around, we're going to need some data components for this. So let's go ahead and define our first data component. And so we can do that by saying public struct, and this is going to be for the character move direction. And this will implement the iComponent data interface. You'll see that by default, the iComponent data is showing up as red. That's because we do need to include the using unity.entities namespace. So this is kind of how we define these data components. So typically we want to do a public struct of data components. So this is going to be an unmanaged data component, which means it's fully compatible with Unity's job system as well as the burst compiler. And this iComponent data interface, basically signifies that this is a component that can be added to an ECS entity. All right, so next up, we're going to go ahead and actually add some data to this data component. The idea here is that we want to include a data type that stores the XY direction of where characters should be moving at any given time. And then in a move system, we're going to use that as input data to know where to actually move our character. So the type that we're going to be using is a public float2, and we can just call this value. So a couple things here. So float2 is actually part of the unity.mathematics namespace. And so float2 is very similar to a vector2. It's just a single data type that consists of two floats, one for the X value, one for the Y value. And then I've also decided to call it value. You see that that's a typical pattern that I use when I create a data component that just has a single variable in it. And it just makes a little bit more sense when you're typing things out, where to actually get this character move direction, we can just say character move direction dot value, rather than being redundant and saying, character move direction dot character move direction. And then we're going to go ahead and create one other data component. This will be a public struct called character move speed. This will also be an iComponent data. And on here, we'll just have a public float called value. And so in this case, this is going to define how quickly our character is actually going to move throughout the game world. Now, it is entirely possible to have both these values be on one single shared component. The reason in this case that I've chosen to separate them out is this character move direction. This is going to be constantly updated with the direction that the character should be moving. For the player, pressing the W, A, S, and D keys. And then for the enemies, it's, figuring out where the player is and moving in that direction. Whereas the character move speed, this value is basically just going to be fixed throughout the duration of the game. So it is nice to kind of have this separation between data components where data is frequently changing versus data that's going to be staying the same throughout the duration of the application. And this kind of leads into some of the things related to data dependencies and, reading and writing to certain components and some of the optimizations that can be made around that. Not going to be going too deeply into that, but again, just the point is to have this split between data that's frequently changing versus data that's not changing that often. So at this point, we've just defined the data components that we want. We're not actually adding these to any type of entity. So let's go ahead and do that now. So this will actually be inside the character authoring. We'll go ahead and create a nested private class here, and we can just call this Baker, and it will implement Baker. And inside these type brackets here, we'll pass in the type of the authoring component. So in this case, it's character authoring. And then inside this class here, you'll see that we do have this red squiggly line, and that's because we need to do a public override void called bake. And then the type in here is, again, the authoring type. So this is character authoring. And then we can just call this, say, authoring. So let me just take a step back and kind of explain what's going on here. So this character authoring, this is going to be a regular mono behavior component added to our authoring game object inside of Unity. And inside this Baker, this kind of defines how we actually take this authoring data that we've defined and convert it over into ECS. So the first thing that we're going to do inside this bake process here is get a reference to the entity that's being baked. So in this case, we can just say var entity equals get entity. And then in here, we need to pass in what are known as the transform usage flags. So the transform usage flags essentially define the ECS transform components that are added to an entity. The one that is most often going to be used are transform usage flags dot dynamic, and this is going to add all the data components necessary for this being an entity that can move around within the world, as well as be part of transform hierarchies. So it can be a child of another object, or other objects can be children of it. The other one that we're going to use a little bit later on is the transform usage flags.none. And that just basically means, hey, don't apply any transform data to this component because it is a data only entity and we don't need to worry about its world position or anything of that nature. So anyways, once we have the entity, let's go ahead and start adding some components to it. So we can just go ahead and use the add component method here. And the type that we want to add is the character move direction. And then inside the parentheses here, we can say we want to add it to this entity. And so in this case, what's going to happen is this character move direction is now going to be added to our entity, but it's just going to have some default values for float2. And that's totally fine because we don't need to initialize it with any special values because during runtime, we're going to be constantly writing to this character move direction. Now for character move speed, we need to do things a little bit different because we do want to define the character move speed through authoring. So we can just go ahead and say add component again. This time we're just going to go right to the parentheses and say entity because this is the entity that we want to actually add the component to. And then just go ahead and say new character move speed. And then here we can actually define the values on the character move speed. So we can set value equal to, say, a value of 5. So when we add this authoring component to an entity, it's going to add the character move direction with 0 zeros for its value here. And then character move speed is going to set to a value of 5. So let's come back over to Unity, go ahead and select the player. We'll go to add component, and then we can now add that character authoring component. And you'll see this character authoring component just doesn't have any fields on it or anything. And when we actually go to enter play mode, we still do have our player character selected. And we can go over to the runtime mode here, and we can start scrolling down, and we do see that we have this character move direction, again set to 0, 0, and we do have the character move speed set to a value of 5. Now if you want, you can actually go ahead and change this move speed and character move direction in here, but right now these data components aren't actually doing anything, they're just data. Now one thing that would be nice to have is the ability to adjust the character's move speed through Unity, so that way we can easily assign unique values to all of our different entities. So let's come back over to our code editor, and on the character authoring component, we'll go ahead and create a public float for move speed. And then, so that is going to expose a move speed value in the editor, and then we can kind of set that through there. Now to actually use that, let's go down to the character move speed, and then we'll set value now equal to authoring.moveSpeed. And so this authoring right here, it comes from the bake method right here, because again, we're defining this with this authoring type. So it knows to look at the associated character authoring script and get the actual move speed that we set in here. So back in Unity, you'll see that our character authoring now has a field for move speed, and let's set this to a value of 3.5. And then now when we enter play mode and swap over to the runtime mode, you'll see that the character's move speed is now a value of 3.5. Now I should also mention a cool little thing about the authoring and baking workflow is if we do go back to the authoring side of things and we were to change this move speed, now it's up to 15.39. We can actually go back to the runtime and you'll see that the character move speed does get updated. So that's kind of the nice thing about working with Unity in the editor here is that anytime we change any values inside the inspector, it will trigger a rebaking process and essentially update all those runtime values. Now, interesting enough, you will notice that when I exit play mode, you'll see that my move speed stays the same. It doesn't like revert to any previous values like you would typically expect in Unity. The reason for this is because when we're re-triggering baking, that data is actually baked into the subscene, and that subscene is just an asset, and the data on that asset is exactly the same when you're in play mode and you're outside of play mode. So if we do want to reset this, we can just set it to say 3.5 how we had it, and then let's go on to actually move our character around the game world. So I'm actually going to show you the incorrect way to move characters around the game world, and then show you the correct way after that. So what I'll do is under this character authoring mono behavior here, I'm gonna go ahead and create a new line and just kind of scroll this out of view here. And so we'll be creating our first system, which is a public partial struct called character move system. And this is going to implement the iSystem interface, just like that. So a couple things to point out here. The reason we use the partial keyword is because Unity uses code generation to take all of the code that we're actually typing into this system here, and it does some code generation on it to actually write more efficient code from us. So that is kind of one of the interesting things about how Unity ECS works, is when we create systems in this way, our code is not actually the code that's being executed. Unity is actually generating its own system code that uses a lot of the kind of lower level APIs that are way more verbose than the current system APIs. And that is actually doing the things to modify the entity data. And then this iSystem interface, this is a system, meaning that it's going to run on any type of data that we kind of define as our input data in our entity query. And it's going to run against that data and perform any data transformations that we are also going to be defining here. So let's go ahead and create an update method here. So we can say public void on update, and we have to say ref system state. So on update, this is similar to just an update in a regular mono behavior. This is going to get called every single frame. And then the system state has some things kind of associated with the system that are required. In some cases, we are going to be using some things off this system state. Other cases, we don't need to. But having this system state as an argument is still required for some of the code generation stuff that Unity does. So now let's create the transformation to actually move these entities through the world. So the first thing that we're going to need is delta time. And of course, we're just going to be multiplying by delta time to sort of normalize for frame rate. There is actually a little bit of a different way that we get delta time in Unity ECS rather than regular Unity game objects. And we can use this system API.time.delta time. Now the system API is a really nice type to have. It's going to kind of provide a lot of nice little helper functions to us. And we're going to be using a bunch of these throughout development here. So this one, again, basically just gives us the delta time of the current frame time. And just multiplying by delta time will allow us to normalize our movement for frame rate here. So we're going to go ahead and create what is known as an idiomatic for each. So we can just use the regular for each keyword. And then here we need to define a variable. I'm just going to go ahead and put a temporary name there for now, and you'll see why in just a second. And then we actually define the collection that we're running against. So we'll say in, and then we'll again use our nice system API to create an entity query right here. And then inside these type brackets is where we actually define the components that we want to query for. So we're gonna say, hey, find me all entities that have these specific components. So the first one that we're going to look for is this local transform. And by the way, you will see that it shows up in red, and that's because we do need to include the using unity.transforms namespace. And so the local transform, again, this is going to have our current position, and we're going to be able to update it to our new position. After that, we do also want our character move direction, and that's so we know which direction to move into on the given frame. And then finally, we'll also want our character move speed, so we know how fast to move in that particular direction. And so there is one additional thing that we need to do, and that's specific to this local transform type. Now, as I mentioned, in this system, we're going to be updating the position of our local transform. Now, when we typically define our entity queries like this, it does not allow us to actually write to the underlying data on here. Again, this kind of goes back into some of the data dependencies that Unity keeps track of, where it needs to know what types are being written to and what types are being read from in any given system, so that it can, order things around properly to, make sure we don't have any race conditions where, like one system is trying to write to data that another system's reading from at the same time, and it can just end up in some weird situations where unexpected things start to happen, which of course leads to very poor player experience. So what we need to do is actually add a specific type, which is called the ref RW. And then we kind of put this local transform in those angle type brackets there. And then the idea here is this basically gives us read and write access to that component. Now we'll come back to my little temporary variable name here. And so actually what's happening here when we're defining this query with these 3 separate components, this type you'll see is actually a tuple type. So it is a type with 3 different kind of like subtypes under it. So the first one is the ref RW for the local transform. The next is for the character move direction. And the final one is for the character move speed. Now, if we want, we could say ASDF.item1 to get access to that local transform, item 2 to get access to the character move direction, and item 3 for the character move speed. But that's like kind of annoying. You don't want to have to do that. So luckily what we can do is instead just delete that and add in some parentheses here. And then here we can just define nice names for each of these variables. So for the local transform, we can just call this transform. For the character move direction, let's just call this direction. And then for the character move speed, we can just call this speed. So then now we have access to all the data that we need. Now what we need to do is actually apply this data transformation. So again, if you'll remember this character move direction, this is in a 2D XY type, and this local transform, the position that we're updating is going to be in a 3-dimensional type. So what I'm going to do here is the first thing I'm going to do is say var move step 2D. And then we're just going to figure out, how much we need to move in a 2D direction on each frame. So we'll just go ahead and say direction.value. And I should point out that, what's happening here is when we're accessing this direction, we're accessing this character move direction type. And to actually get the underlying value, remember that we named the value. So we need to actually say .value to get that underlying value. So here, then we can also go ahead and multiply by our speed.value. And then multiply that all by delta time. So again, that's just, us figuring out how much we need to move on a 2D plane each frame. Now we need to actually go ahead and modify our transform. So unfortunately, we can't just say transform.position just like that, because what's actually happening when we're accessing this transform is we're accessing a type of ref RW, and then kind of the subtype of that is local transform. So we actually have to say transform.value RW.position. And then the idea here is, with this value RW, we're accessing this local transform type, giving us write access to it so we can update this position. So here we can update the position by saying plus equals new float 3. And again, this is a float 3 type, similar to a vector 3 within regular Unity. It just has 3 floats for X, Y, and Z. And then the nice thing about converting a vector 2 from 2D to 3D is if we're moving in the XY plane, we can just say pass in the move step 2D. And then we also need to pass in a Z value, and we can just pass in 0 because we don't need it to move on the Z plane at all. So anyways, that's actually all we need to do to move our character throughout the game world. So let's go back to Unity and test this out. So we'll go ahead and enter play mode, and you'll see nothing happens. Our character is not moving at all. And that's because we're not actually setting anything for the character move direction. Now we're going to be getting into doing player input in just a second, but we can still test things out here by going over to our runtime mode and looking at our character move direction. And let's just set this to a value of 1 in the X direction. And you'll see that our character starts moving. Hooray! So actually you will remember that I did mention that I was going to show you the incorrect way to apply movement. And while yes, this is simple and it looks like our character is moving nicely along the screen, there is actually one major problem with it. So what I'm going to go ahead and do is grab one of these boulders right here and place it just directly in front of the player. Now, actually, before we test this out, there is one thing that I completely forgot to do, and that is to set the layers, the physics layers for all of our entities. So we can just go ahead and highlight all of our boulders, and we'll change this to the environment layer and go to our player and change that to the player layer. And then now, based off of the collision matrix, players and environment elements should be able to collide with each other. So let's go ahead and enter play mode and give it a test here. So we'll go back to the runtime here and set the character's move direction to a value of 1. And you'll see that it just moves right through that boulder like it was not even there. And even if we say, change this move speed down to a quite low value and, tried to move right into that boulder again, you'll see that we just move immediately right through it, which is not exactly what we want to happen. Now, the reason that this is happening is because when we're actually applying movement in this way, where we're adding to the transform position, well, what we're actually doing is a teleportation move. And that basically means that we're saying, hey, let's take this entity and move it from this position immediately to this position. And even though we're kind of, constantly doing this on a very small amount, so we're, moving it only very slight movements, we're still kind of doing a teleportation move saying, hey, move this to this frame, move this to this frame, right? And so because we're constantly overriding this local transform value, it actually does not give Unity a chance to resolve these collisions, to separate the two entities apart. So in order to actually get this to function properly, we need to use Unity's physics system to apply the movement rather than doing the movement directly on the local transform like this. So instead, what we're going to do is we're actually going to modify the character's physics velocity component, and then we're going to basically have Unity handle all the collisions and everything like that. Let me just temporarily set the linear physics damping to 0, and that'll allow me to set a linear velocity of 1. And you'll see that the player should go right up to the boulder, collide with the boulder, and then stop moving. So let's come back to our character move system, and we'll just do a little bit of refactoring on this. So rather than the local transform, again, we're going to be writing to the physics velocity component. So this is a component that Unity adds automatically when we have that rigid body component. And so this is kind of what Unity uses to determine how things should be moving throughout the world. And to actually get access to this, we do need to, instead of using Unity's transforms, we can use unity.physics, and then we can update this from transform to be velocity. And so we'll actually be handling velocity a little bit different. So I'll just delete out this whole line. So we can just say velocity. Again, we do need to do the value RW because we are writing to it. Dot linear because we're just setting the linear velocity, and rather than doing a plus equals, we'll just do an equals because we're just saying, hey, this is the velocity that it should be at this frame, and we don't want to increase the velocity. We're not applying an acceleration force or anything like that. We're just saying, hey, this is the velocity that should be at. So again, we're just going to do something similar where we can say new float 3, pass in our move step 2D for the first argument, and then 0 for the second argument, because again, we don't want it to move on the Z plane at all. Now, one thing with setting velocity in this manner, again, we're just setting the direct velocity. This has nothing to do with frame rate. We're just saying, hey, this is the speed that it should be moving at. So actually, we do not need delta time. So we can just actually remove that altogether. And then our move step 2D is just the direction.value multiplied by the speed.value. And then again, just kind of applying that linear velocity directly. So back over to Unity, go ahead and enter play mode here. And we can switch over to our runtime inspector for the player, and we'll set our character's move direction to be a 1 in the X direction, and you'll see that it moves nice and quickly and then runs into the boulder and then just stops right at the boulder, which is exactly what we want to see. So at this point, we want to give the player the ability to actually move the character around through the gamer world. It's kind of annoying to go into the inspector and just edit directional movement values. We actually want to use the WASD, arrow keys, joystick, whatever, to move the player throughout the game world. So let's go ahead and do just that. So I'm going to go to the settings directory. I'll do a right click, create, and go down to input actions. And we can call this, say, survivors input. And so we'll go ahead and double click to open up the survivors input. And you should see a nice little window like this. Let's go ahead and create a new action map. This will be for the player. And then I'll go ahead and just delete that action because we don't need it. And we'll just create a new action here, and we can call this move. And then the action type is actually going to be a value. And then for control type, we want to say vector2. So this basically means that, we're applying input in a vector2. So we're looking for X and Y input, where the X input is, say, moving left and right, and the Y input is moving up and down. So this is just us kind of listening for this input, and then we can convert it over into our ECS data as needed. So we'll go ahead and open up this drop down and create a new binding here. So we'll add an up, down, left, right composite. And then you'll see that we have this 2D vector right here. I will point out that, again, the composite type is a 2D vector, and the mode is set to digital normalized. The nice thing about having digital normalized is that this means that if you're saying holding up in a diagonal direction by pressing the W and D keys, then it's going to normalize that vector to just be a factor of 1. So we don't end up in the problem where, if we're going up diagonally, then the X is a full 1 value and the Y is a full 1 value. Those are normalized to be a value of 1. So it doesn't matter, what direction that we're moving in, the players will always be moving at the same speed. So here we can kind of define all of our bindings. So for up binding, we can press the W key, down, go to listen, and do the S key, left, listen, A, right, listen, D. Go ahead and duplicate this. And actually I can rename this 2D vector here to WASD, and this one to arrow keys. And then here I can just define all the different arrow keys for up, down, left, and right. So then once we're done, just go ahead and click Save Asset. And that's actually the only input that we're going to need, because this is a Survivors type game, and in Survivors games, the player can only move, and that's all they can do. So when we do have this Survivors input selected, we do want to make sure that we check mark the box for Generate C# class and click Apply. And then Unity should recompile here. We do need to do that because when we're gathering input from the ECS side, we do need to read the generated C# class file in order to actually read that movement data and apply it to our character movement. So again, here's where we kind of reach a little bit of a split, because we started out with this character authoring, which again is going to be able to apply movement to both player characters as well as enemy characters. So now we want to kind of start to split things up, where we can kind of have a player take in input from the actual keyboard presses from the person playing the game, and then the enemy, it should kind of take in its own input from its AI logic. So we kind of need to split things out to have a specific character now. So I'll come over to scripts and I'll just create a new C# class here, and I can call this player authoring. So I'm first going to just include a couple namespaces that I know that I'm going to need. So I'm going to need Unity Engine and Unity.entities. And the first thing that I'm going to do is create what is known as a tag data component. And so we just define one of these by doing a public struct. We can call this player tag, and this will also implement iComponent data. Now with this, the special thing is that it doesn't have any actual data components in it. It's an empty data component, which is known as a tag data component. And this is going to allow us to basically find the player entity just by querying for any entity with the player tag. So let's go ahead and actually add this to a player entity. So we'll need to turn this player authoring into a mono behavior, and we'll go ahead and create that private baker class here. And then same thing as before, we do want to get a reference to the actual entity that we're baking. So again, we can just say get entity, passing in those transform usage flags. Again, we're going to be using the dynamic transform usage flags because we want the player to have all those usage flags as well. And then here we can just go ahead and do an add component, and we'll add that player tag to the entity there. And so that's all we need. We don't need any like special additional data components to create our player input system. So let's go ahead and do that now. So this system is going to be defined a little bit differently than our previous one. So this is going to be a public partial class this time rather than a struct. And we can call this the player input system. and this is going to be a system base. So these system base type systems are a little bit different. It's typically preferred to use the I systems, which are the previous system type that we did. Now, these system base type systems, they work similar with some syntactical differences. One of the reason that I'm using a system-based system here is because with system-based systems, we actually can have managed types be member variables of the system base itself. Now, it's typically not best practice to have member variables for systems at all. Typically we want that nice separation between data and systems. However, for the case of input systems, I usually make an exception because it's really easy to just create an input system object and have it be a member variable of the system, and that way we can read input from it really easily. So I'm sure this red line is probably bothering you, so I can just do one of these to implement the required member, which in this case is just the protected override void on update. So you see that, again, slight differences with the system base. It's a public void, whereas this is a protected override void. And this one does not take in that system state as a parameter. It doesn't take in any parameters, actually. So what I'm going to do is I'm going to go ahead and create that member variable here. So we'll say private survivors input, and we can just call this underscore input. And then, so we need to actually go ahead and create this input action. So we'll go ahead and create another protected override void. This one is called onCreate. And then in here, we can actually create the input actions just by doing underscore input equals new survivors input. And then we could just do an underscore input dot enable, just like that. So now in the on update, which is going to be ran every frame, let's go ahead and actually read input each frame. So we can say var current input is equal to our input here dot player. Again, we're accessing that player map, and we want to access the move action on the player map. And to actually read the value, we can just do a dot read value. And we do actually have to read this as a vector2 type. And then what I like to do is just cast this to a float2. Again, we are going to need the unity.mathematics namespace in order to use float2. And then that way it's already available for us as a float2. And then we can just set the player's move direction. So the way that we're going to do this is do another of these for each queries. And in this case, I know that we're just writing to that character move direction. So we can just say direction in system API.query. Again, we're writing to this, so we need to do the ref RW, and it is the character move direction type, like that. And then, so if we're to do just this, then it's going to be a little bit of a problem, because when we get to having enemies later on, then this is also going to be writing to the enemies. So instead, what we can do is also specify that we need the with all player tag, just like that. And this means that the query is only going to match for any entity that has the character move direction and that player tag. So we know that we're only writing to the character's move direction. So here, all we can do is just do a direction.value.rw.value is equal to the current input. So super easy. We're just applying the inputs directly to that character's move direction. And now we'll come back to Unity. We'll select our player and make sure we go to the authoring mode. And we will need to add in that player authoring script on there. And again, actually, we can look in the entity baking preview right here. And you can see that we are adding, the character move speed and direction right there. And scrolling down, this also shows that we're adding the player tag as well. So now we are good to enter play mode, and you'll see that our character is stationary right now. And then if we start moving around, hey, look at that, our player starts moving around the screen. Now, luckily, when we still run into these boulders, it'll stop us just fine. However, if we hit the kind of corner of the boulder, we can kind of start rotating around like this, and we don't necessarily want that to happen. You'll see actually I started kind of rotating towards the camera. So I'm on just like a totally different rotation plane, And that is not looking good. So we need to fix this ASAP. So what's kind of happening here is, again, when we switched over to this movement where we're just setting the physics velocity, we're telling Unity to say, hey, you take care of handling all the collisions and everything like that. And it says, cool, I got you. And then, so not only does it make it so we actually stop when we hit a wall, but it also is like, oh, hey, if you hit a wall, you probably want to apply some rotation there. And in most 3D games where something hits something, it's nice to have it kind of rotate off in a nice way. However, in a 2D game like this, we want to be like, no, we actually want to be in complete control of rotations. In fact, we just don't want it to rotate at all when we hit things. And if we do, then yeah, maybe let's do that rotation manually. But we're like, hey, Unity, don't worry about doing the rotation stuff for collisions like that. So the way this is actually accomplished is we can look into the runtime inspector here and scroll down, and you'll see that we do have this physics mass, and there is this option for inverse inertia. And you'll see that it has some values set on here right now. We basically just want to say, hey, we want essentially infinite inertia. So the if we just set 0, 0, 0, so the inverse of inertia is 0, 0, 0, then that means that now when we move around the game world and collide with the different boulders on the corners, now we're actually not going to be rotating. Again, we're just kind of like disabling that feature essentially. Now, luckily, this inertia value isn't something that is constantly changing throughout the duration of the application. All we need to do is just set this value once inside of an initialization step, and then that value is just going to be set for the rest of the application. So this is kind of a nice little concept that we'll be going into, where we can use what are known as enableable components and use those to do some initialization logic. And again, we want this behavior to apply to both player characters as well as enemy characters. So we're going to be doing this in the character authoring level. So in the character authoring, up at the top, we'll go ahead and create a new data component here. So this is a public struct called initialize character flag. And this is an iComponent data. We do also want this to be an iEnableable component. And this can just be an empty component here. So that's kind of like one of the patterns that I use is, we have tag components, which are empty data components. And we also have flag components, which are empty data components, but also have this iEnableable component on here. To explain how these enableable components work, it might be easier if I just go ahead and add this to the character right here. So we can say add component, initialize character flag, and of course add that to the entity. So now when we enter play mode and go over to the runtime inspector for the player, you'll see that up top it lists all the tags. So these are the empty data components. So you'll see that we have the player tag here, and then we also have the initialize character flag, and you'll see that there is actually a checkbox next to it. And so this can be either enabled with the checkbox selected or disabled with the checkbox unselected. And so I should point out that this type of behavior is not unique to just empty tag components. If we scroll down, you can see Unity has this material mesh info as an enableable component. And so we can enable, disable it by selecting this checkbox. And you see that actually when we disable it, the character is no longer being rendered. And then when we enable it, it is being rendered. So that's kind of the cool thing about enableable components is we can use it as a way to query for a specific component that has a component, but also has that component enabled. And I don't know how much I want to get too deep into the technical details about some of the optimizations that Unity can make as far as enableable components, but this is typically a better approach to enable and disable components rather than adding or removing components, basically because adding and removing components induces what's known as a structural change. And that's a decently expensive operation because we actually need to take entity data from one place of memory and move it into another place in memory. And it incurs like a sync point, which makes all our jobs stop. So it's something that we're not going to get around eliminating structural changes, but we just want to limit the number that we're doing. So anyways, back to this initialized character flag. The idea here is we're going to look for any character that has this initialized character flag, we're going to have them go through that initialization step where we're setting the inverse inertia. And then once we're done with that, we can disable this initialized character flag so that that initialization step will only happen one time and it's not like continuously running. So above this character move system, let's go ahead and create a public partial struct. This will be the character initialization system, and this will also be an I system. And then inside here, we'll do our typical public void on update, ref system state and state. And so one cool thing that I'm going to do with this particular system is we're going to tell this to actually run towards the beginning of the frame. So we can specify that we want this to update in group type of initialization system group. And so Unity has some of these like high level system groups defined. So there's kind of the initialization system group, which happens at the beginning of the frame. There's the simulation system group where most of our code logic is going to be stored. And if we don't specify a system group, it goes into this simulation system group. And then finally, there's the presentation system group, which happens towards the end of that player loop. So we're going to say, you know, any of our character initialization, we want this to run early on in the frame because when we actually go to spawn new enemies, we're going to spawn those at the beginning of the frame. And we want this initialization process to run before any of their additional actual game logic runs. So let's create our for each here, and we can say var ASDF for a little placeholder there. And we want to go in the system API.query. And again, we're going to be writing to a specific component. So we're going to be writing to the physics mass in this case. And another thing that we can do is to query for these enableable components. We can use another special keyword here, which is the enabled ref RW. And in here we can pass in the type, which again is the initialize character flag. And then we can just kind of close out that query right here. So the idea here is that when we define this query like this, with this enabled ref RW, this means that in order for an entity to match this query, this initialized character flag needs to be enabled. And by using this enabled ref RW, this gives us the ability to disable this component from inside this system. There are other different ways that we can go about querying for enableable components and enabling them and disabling them. But in this way, it's nice to kind of streamline both those functionalities into just this one little block of text right here. So let's go ahead and change our placeholder. Again, this is going to be a tuple. So for physics mass, we can just call this mass. And then for the initialized character flag, let's say should initialize. So inside the for each body, we can say mass.value RW because we're writing to this value. And we want to specifically write to the inverse inertia. And we'll set this equal to float3.0. And again, we're basically just zeroing out that inverse inertia, which basically just disables the ability for things to rotate after collisions. And then finally, we just need to disable that initialized character flag. So again, we can access that with the should initialize. And then similar to the ref RW, we can also do a value RW and then just immediately set this equal to false. So this kind of allows us to set the enabled state of a component. So it is a little bit weird because it's a similar syntax to the ref RW where we access value RW, but we're not accessing a specific variable. Just by doing this should initialize.value RW equals false, this is going to disable the initialized character flag. So now we can come back to Unity and enter play mode. And you'll see that already the initialized character flag has been disabled because that just happens immediately on the first frame of execution. And scrolling down, if we find the physics mass, you see the inverse inertia is set to 0, 0, 0. So let's go ahead and test out our game here. And we can move over onto the corner. And you'll see that we are no longer moving around in any weird rotations. The collisions are all working exactly as expected. So anyways, that is kind of, how we can actually get this player moving around. But there is actually one final thing that I do want to showcase with the character move system before we move on to some other fun things. What we can actually do is, because we're only using just regular, simple, unmanaged data types on here, is we can actually enable the burst compiler just by saying burst compile, just like that. Right above the on update. And you do see that we also need to say using unity.burst, and that gives us access to utilize the burst compiler here. If we want, we can technically add this to our character initialization system, because again, we're all using unmanaged type on these things here. But yeah, this is going to give us much better performance for these particular systems. The character move system is going to be a much more important one to have it on, because this one's going to be constantly running throughout the duration of the application on, however many enemies we end up having. And so we can go back to play mode here, and we can still just move our character around as expected. However, our character movement is now running with the burst compiler. Okay, so now that we got the character moving around, the next thing that we're going to do is actually get the camera to follow the player. Now we're going to do this using Cinemachine. Now, Cinemachine, of course, is a regular Unity game objects concept. So we're going to need to have a little bit of a bridge between the ECS side of things and the game objects side of things. Because we actually, unfortunately, can't have direct references from the things in the ECS subscene to things in kind of our main scene. So we end up having to do a little bit of a workaround to kind of get this behavior to be working as expected. So what I'm going to go ahead and do is just kind of in the main scene right here, I'm just going to go ahead and create an empty game object, and I can call this the camera target. And then from here, we can just go ahead and reset its position and all that. And then I'm going to go to the Cinemachine camera and set the tracking target equal to that camera target right there. You can see that these are all the other values that I have on here, and I do have the Cinemachine follow set with a follow offset of -10 in the Z direction, and so that basically moves the camera 10 units away from our camera target here. So our camera target here is just kind of at the center of the scene, and you'll see that as I move the camera target around, now the camera moves around the world. Now, what we want to actually happen is that as our player moves around, we want our player to tell the camera target where to move, and then the Cinemachine camera is going to follow the camera target. So it's kind of a little bit of a chain of hierarchy here. So what we're going to end up doing is, again, have a little bit of an initialization step for our player to essentially find this camera target. Once it finds this camera target, then it's going to store a reference to it. And then every frame, we're just going to update the position of that camera target based off of the player's world position. So let's get into it. So first thing I'm going to do in scripts is I'm just going to go ahead and create a new Unity script here. And I can call this the camera target singleton. And then I'm going to go ahead and create a singleton out of this by using the public static keywords for the camera target singleton type, and just call this instance here. And so I'm just going to go ahead and create a pretty simple singleton mono behavior script where if there's already a singleton instance, we'll just go ahead and destroy the new one and print out a little warning to the console. Otherwise, we'll just go ahead and set the instance equal to this. And then come back to Unity, and we'll just go ahead and add this camera target singleton to the camera target. So let's go ahead and create a new data component, and this would be a public struct, and we can call this camera target. And this will be an iComponent data, of course. And in here, we will need a public Unity object ref of type transform, and we can call this camera transform for now. So anyways, Unity object ref, as you can imagine by the name, this allows us to reference Unity objects from the ECS side. Now you'll notice that this is a public struct of iComponent data. There also is a concept of managed data components that uses a public class of iComponent data, and we can have just references to any managed types within there. However, the advantage of using this Unity object ref is we can have just a regular unmanaged data component, and this Unity object ref essentially just acts as a pointer to this camera transform in this case. And so with these Unity object refs, we can reference any Unity object type, whether that be a game object, any component type, any scriptable object. And so it kind of provides a nice link between the ECS and game objects worlds. Now, the cool thing about these is that these data components are not subject to, certain restrictions about the job system and burst compiler. However, when we actually access the underlying data, in that case, then we're not able to utilize the job system and burst compiler for those things. But if we do have, say, other values inside this camera target, and we want to reference those in a fully bursted context, we can totally do that. So Unity Object Ref is a really handy way to, reference Unity objects. So once we have our camera target defined, I'm going to show you actually an alternate method of doing an initialization step. So we can do a public struct for initialize camera target tag. And this also is going to be an iComponent data, and it's just an empty iComponent data because it's a tag component. And we're just going to go ahead and just add that initialize camera target tag to our player entity. And then I'm also going to go ahead and add component for the camera target itself. And we'll just assign this to the entity. So right now, this pointer in here is effectively going to be empty. And then during our initialization step, then we're actually going to add the camera target in here. And then above this player input system, I'm going to go ahead and create a new public partial struct for the camera initialization system. And this is an iSystem. And we do also want this to update in group type of initialization system group. And a cool little optimization that we can do by having this initialize camera target tag is actually in the public void on create. This also, by the way, does need a ref system state called state. We can here actually use this system state by saying state.require for update and pass in the initialize camera target tag. So this basically means that when we go ahead and create our public void on update, this means that this update method will only run when a entity with this initialize camera target tag exists in the game world. And so what's going to happen is we're going to run our initialization step, and then we're going to remove this component from the entity, and then this system is no longer going to update. So inside the on update, let's just go ahead and check to make sure that camera target singleton instance actually exists. So if it's equal to null, then just go ahead and say return. So this basically means that, if the camera target singleton does not yet exist in the game world, we'll just go ahead and try again on the next frame. The reason behind this is because sometimes the ECS world and game objects worlds loads at different times. So this provides a little bit of protection to say, hey, let's actually make sure that this camera target singleton exists before we try and get a reference for it and save a null reference, which we don't want. So here, let's actually get a reference to that camera target transform. And we can get that from the camera target singleton dot instance dot transform. And so once we have that transform reference, we can actually assign that. So then let's go ahead and create this for each here, little placeholder, of course, in system API.query. And we do need to write to that camera target type. And we also want to say with all of the initialize camera target tag, and just force to make sure that it also has a player tag as well. So now let's go ahead and set the camera target right here. So we can say camera target dot value RW dot camera transform equals to the camera target transform, just like that. So that's actually us assigning the reference. Now it is a little bit interesting. I'll kind of point out that we're actually assigning this to the Unity object ref type, but Unity kind of implicitly assigns this to that underlying transform pointer that we're saving. So that's all we need to do for our initialization step. Now we need to remove this initialize camera target tag from the player. So we actually have to do this inside this for each loop here because we're kind of iterating over the player. However, we can't just, use like say the entity manager or something like that to remove the component inside this for each, because that ends up changing the entities that we're querying against, and it, ends up throwing some errors in the editor if we try to remove this component while we're iterating over this collection. So what we actually have to do is use an entity command buffer. I usually just call these ECB. And so we can just create a new entity command buffer just by saying new entity command buffer. And then we do have to pass in an allocator. And the allocator I recommend using for temporary things like this is the state.world update allocator. So if you're at all familiar with the different levels of allocation that Unity has, so there's temp job, and persistent. And so temp is just, when we need some temporary bit of memory, just to be kind of used within a method like we're doing here. So state.world update allocator actually works similar to the temp memory, but it is a little bit more efficient because it's technically like a rewindable allocator. Essentially, my understanding of it is that this is a block of memory that is available to us to use that is going to get cleared out every frame. So rather than using temp memory where we're creating new blocks of memory, this state world update allocator allows us to reuse that same block of memory over and over and over again for simple little things like, creating an entity command buffer where we need to, just remove one component. So we actually do need a reference to the entity itself in order to remove a component from it. So at the end of this whole query, I'm going to do another .with entity access, and this provides us access to the entity. So now this changes our camera target because it now becomes a tuple. So we have to put the parentheses around it here and also add in the entity as one of the arguments there. So here we can say ECB.remove component, and here we want to remove the initialize camera target tag, and we're just removing that from the entity. Now, this doesn't actually remove it, it just kind of records the operation of removing it. So the final step we need to do is do an ECB.playback, and in here we can pass in the entity manager. So we say state.entity manager. And then, so we need to make sure to do that outside of this for each loop, so then it actually plays back all the operations that we've recorded inside this entity command buffer. So then we'll come back to Unity and enter play mode, and you can see that we can still move our character around. Now the camera is still not following the player because we're not saying any, we don't actually have any logic in place to actually move that camera target yet. However, we can check on a couple things here. So if we actually go over to the player and in the runtime mode, we can actually see the initialize camera target tag is not showing up inside the tags here for the player, which is good. And if we go down to the camera target, we can see there's a camera transform, and the ID is set to an instance ID of -73250. Now, unfortunately, the way that this kind of like pointer reference works is via these instance IDs of these Unity objects. So it doesn't like give us a thing that we can click on and say, hey, go to that object. So we'll just remember this instance ID of -73250. And if we go to the camera target, we can do the little 3-dot menu kind of in the upper right of the inspector and go to the debug inspector. And we'll see that the instance ID of this camera target does line up to that -73250, specifically for the transform of that camera target. So again, we're storing a reference to that transform. So now that we have a reference to the transform, all we need to do is now just update its position based off of the player's world position. So let's go after this camera initialization system, and we'll create a new system. So this is going to be the public partial struct called move camera system. And this of course is going to be an I system. And so we'll go ahead and do a public void on update ref system state, and we'll create our for each here. The temporary name in system API dot query. So now, remember, we're going to be looking for the player's world position and then applying that to that camera target transform. So to get the player's world position, we could technically use the local transform because we don't have the player doesn't have any parent. So its local transform is going to be the same as its world transform. But I'm going to show you another way, and this is actually by using the local to world component, which I believe I mentioned kind of early on. And this does require us to use the unity.transforms namespace as well. So the local to world, no matter where you are in the transform hierarchy, this is always going to be your world position, rotation, scale, and all that. And then importantly, to make sure this is actually up to date, let's go ahead and tell this system to update after the type of transform system group. So the transform system group is something built into Unity that basically takes the local transform and any transforms of the parents and all that, and it converts it into this local to world. So, and this local to world is actually what's sent off to the GPU to tell it to render that entity at a specific world position. So again, this transform system, it takes all that local transform data and then updates it into the local to world. So if we update it after that transform system, then we know that local to world component is going to match where that entity is going to be rendered on this specific frame. So we have the world position. Now, again, we just need the camera target here because we actually need to write to that transform. And so let's go ahead and replace our temporary variables with transform and camera target. So to set the camera's target position, we'll say camera target. And then on here, remember, we need to actually access the underlying Unity object ref type, which we named camera transform. And then from that camera transform, we actually need to say .value, and this is essentially us dereferencing that pointer. So this .value actually comes from that Unity object ref. So if we hover over this value, you'll see that it is a type of transform, and this is like the regular Unity game object transform. And then so to actually set the position on it, we can say .position and make sure that's the lowercase p position, because again, we're accessing the Unity transform type, which calls position a lowercase p. And then we'll set this equal to the transform. And again, this is this transform associated with the local to world of the player. So we'll say transform dot position. And again, that's a capital P position. So this is a float 3 and this is a vector 3. Unity can automatically cast one to the other, no problem. I think the last thing that I'll just do real quickly is I'll just say with all player tag, just to really force that we're running it on the players. Even though again, there should only be one of these camera targets, but better safe than sorry. And then I'm gonna further specify this query by saying with none initialize camera target tag, and that way, if the camera target has not been initialized, then this system will not run. So we'll go ahead and enter play mode here, and you'll see that our character is centered right in the middle of the screen, even though he was offset a little bit before, so that's kind of a good sign. And now as we move around, yes, you'll see that the camera is following the player around. So this is very exciting. It's a great step in the right direction. However, I don't know how well you'll be able to see this over on the YouTubes. Let me see if I can zoom in the camera just a little bit here. As we move around, you might be able to see, but our player has a little bit of kind of jittery movement. It's not smooth. It's kind of stuttering and jittering, and it just doesn't look really good. Like, yeah, you can probably see it. It's pretty apparent right there. So yeah, what is going on with that? Well, hey, glad that you asked, because there is actually a really interesting explanation to this. So remember how way back when we changed over our character movement to actually utilize the Unity physics to set its movement position. So again, every frame we're just writing to the velocity component, and then Unity is using that velocity component to actually set its position, again, accounting for any collisions or any other physics things that it might need to worry about. So what's actually happening is Unity's physics system that actually says, hey, this player needs to update to this position at this time, or whatever, that actually runs in the physics system, which runs in a fixed step simulation system group, which means that those systems are only called on a fixed time step rather than once per frame, which were actually being rendered to the screen. Now, this ends up being a little bit of a problem because there is kind of this mismatch between the player's motion, which is only being updated on that fixed time step, and what we're actually rendering to the screen, which is typically a much higher frame rate. So with this discrepancy, we end up getting this kind of jittery movement. Now, luckily, there is actually a quite easy solution to this. So if we go onto our player here, and we go back into the authoring mode and then go ahead and pop open the rigid body here, you'll see that there is this interpolate option here. So this little drop down here, there's interpolate and extrapolate. So if we actually open up the entity baking preview to see all the things that get added here, if we change interpolate over to extrapolate, you'll see that this actually adds this new thing here, which is this unity.physics.graphics.integration.physics.graphical smoothing. And so this actually is a data component that's added that can kind of apply some additional smoothing to the character. If we change over to interpolate, you'll see that we still have that physics graphical smoothing, but there's also a physics graphical interpolation buffer. And so actually we can kind of inspect some of these things here. So the physics graphical smoothing here, this looks at the current velocity, and there's this apply smoothing. And I believe that if this value is at anything above a 1, then it knows to kind of apply some smoothing. And then the physical graphics interpolation buffer, this actually stores the previous transform and previous velocity. So it kind of like either do an interpolation or extrapolation, kind of like based off of its current position and current velocity to figure out where it should be. The whole idea behind this is that this actually kind of normalizes out the graphics for frame rate. So even though the entity is still technically moving on a fixed time step, the graphics don't make it look like that it is, and it should be smooth movement. So we'll go ahead and have interpolate be interpolate, and go ahead and go full screen on here. And then now we can move around, and the movement is way perfectly smooth now. And so if I'm zoomed in on this character here, you'll see that there is none of that frame hitching. It is all perfectly smooth movement here, which is exactly what we want to see. Now with us completely zoomed in on our character like this, it is making it extremely apparent that we don't have animations set up in this project yet. So let's get into character animations next. Okay, sorry for the flashbang, but just real quickly wanted to show this beautiful art asset created by Sil over at Penzilla Design, and just wanted to display kind of how these character animations work. So you'll see that this is one PNG for the sprite sheet, and down along the bottom, we have the walking animation for the astronaut. And then up top, we have an idle animation where it just kind of like bounces up and down just a little bit. So the idea here is this is kind of a flipbook style animation. So we're just going to be kind of like playing through this frame by frame by frame. And then we actually can have the ability to swap between the idle and moving animations when it kind of changes its walking state. So we'll be getting into all this stuff here. And then so on the sprite itself, just for its import settings, it's important that we have the sprite mode set to single, because we're actually not using like multiple sprites to play the animation. We're just kind of having this as one sprite, and then with our shader, we're kind of setting the offset of where it should be displaying things to play the animation and the correct animation type. I also do have the wrap mode set to repeat so that it actually repeats around, because I think if this isn't set, then you can get to like the last frame of animation and it like doesn't display. I don't know, it was kind of weird. Okay, so just gonna go real quickly over how this shader works. Again, this is not really a course on shaders, and I'm not really a shader expert or anything like that, but this shader is the one that I have shipped with the starter project files, so it will be included if you do want that. The idea here is that we're, again, kind of doing our own flipbook style animation, and we're going to be using this for both players as well as enemies in this project. Now, in my full Dot Survivors asset store project, I actually have two separate shaders, one for the players and one for the enemies. And they can actually do a little bit more things than what we have right here. But this is just enough to get, a nice simple walking animation going, and be able to face the character in the appropriate direction and all that. So anyways, just zooming in here, the first portion, we're kind of like figuring out what animation frame we should play. So I do have this global time, global shader property. This becomes more relevant when we get to doing gameplay pausing at the very end. Because there is just kind of a regular time node that we can use, and we can feed this value into this portion right here. However, what ends up happening is the way that I implement gameplay pausing, that time value keeps incrementing, so then the animations still keep playing when the game is paused, and it looks a little bit weird. So I have this global time property here, and we'll be getting into this a little bit more after we just get our kind of like base animations going. The idea here is this is a global shader property, so all shaders kind of share this same value. And then the idea is that I actually have a system to tick this value up. And then when the game gets paused, then we pause the system to tick that value up, which effectively pauses the animation. Kind of moving along here. So then you'll see that we have like, frames per second and frame count. And so this kind of just like takes these things into account when we're figuring out which animation actually should be played. The animation index is just kind of us figuring out the index of what animation to play. So you'll remember that the walking animation was kind of down across the bottom. So that's effectively animation index 0. And then the idle animation was up top, which is animation index 1. And then again, just kind of like figuring out how to slice things up by the tile count and number of animation frames and all this. To set the particular tiling and offset, and then we're just passing this into the UV of our sample texture 2D, and we're just sampling this sprite sheet right here, and this just immediately gets fed into the fragment portion of the shader here. I should point out for a couple of these material properties, such as say the facing direction, this is known as a material property override, and the cool thing about these is this allows us to change the values of these on a per entity basis. So of course, because every entity in the game is going to be facing, either to the left or to the right, and we want that to be handled on an individual basis, we can have this facing direction right here. And you see that when we kind of open up the node settings on here, that we have the name of facing direction, and the reference is this underscore facing direction. And then the scope, we want this to set to hybrid per instance, which means that we're effectively overriding this property on a per instance basis. And the other thing that we need to facilitate with this is if we go to the graph settings, the allow material override box should be checkmarked. So that means that any materials with this shader can have their properties overridden via these material property overrides. And the material property overrides are super cool because it's like all done through ECS, that we can just manipulate these shader things. And so that makes it really nice to kind of do some cool things with these animations just directly through ECS code. So then if we actually go to the astronaut material right here, we can see that we just kind of have some general settings, make sure that we set the alpha clipping on here so it doesn't, render the background. You can see that we're just feeding in the sprite sheet right here. And then here's where we set frame count. So this is like the number of individual frames. The way that I have this shader currently set up is that, it needs to be an equal number of frames for all the different animation types, which is totally fine. Animation index, you see this is set to 0. And then if we set this to 1, he switches over to the idle animation right there. The animation count is the number of unique animations that it has. Again, we just have walking and idle, so this is set to 2. Enemies are a little bit different because they only have walking animations, so it'll be set to 1 for the enemies. Frames per second is how quickly we want this animation to actually play. So this is 12 frames per second. And then you see facing direction is set to 1, means it's facing to the right. And if we set it to -1, he'll be facing to the left. Spawn time just kind of allows me to have a little bit of an offset so the animations can be on different frames. But you can see that, if we drag this, we can get a little preview of what that animation looks like. And heck, I'll even show you the idle animation too here, so you can see it's just kind of bobbing up and down. So anyways, I don't think I'm actually using the spawn time in this tutorial project. However, I am using it in the full Dot Survivors project. So anyways, that's just kind of like an overview about how all this stuff is set up. Remember that the player already has this astronaut material assigned to them. So as far as like materials and shader goes, like that stuff is all set up as part of the starter project files. So now we'll get into the fun part of actually playing this animation. So it's actually going to be super easy to get started because you'll remember that I have that kind of global time shader property to actually increment the time which will actually play these animations. So that's what we're going to do now, and then the animation will start playing, and then we can clean up a couple issues after that. And so I'm actually going to go ahead and go to the very bottom of this character authoring script below the character move system, and we'll create a new system, which is going to be a public partial struct called the global time update system. And this is going to be an I system. And then here we're going to have a private static int for the global time shader property ID. And inside the public void on create, we can go ahead and set this global time shader property ID equal to shader.property2id, and then we actually need to pass in the reference string for the global time. If you may remember, that was underscore global time. And then the idea with this is we're basically just caching this integer because we are going to need to, inside the public void on update, because actually every frame we're going to be doing a shader.set global float, and here we can actually just use that cached integer, which is the global time shader property ID, and then we can just set this equal to system api.time.elapsed time. Now this is going to get mad at us because elapsed time is actually a double. So we'll just need to cast this to a float. So basically the system, we're just caching the property ID for that global time string. And then each frame we can set the global property via that cached integer to the current elapsed time of the game. So now we'll enter play mode and you'll see that our character starts walking. So this is very exciting stuff because now now that we're updating that global time property, as it continues to update, then the animation is able to progress, and we have this nice little walk cycle. Now, obviously, a couple issues with that. Our character is not moving, but they're still playing that walking animation. So here we want them to actually play that idle animation. And then also, as we walk around, we're only facing to the right. So even if we're moving to the right, we're still walking this way. So we're kind of like moonwalking right now. And yeah, that's, cool, but not exactly what we want. And then, so yeah, we need to kind of resolve those two things where we're playing the correct animation as well as the correct facing direction. So let's go ahead and tackle both of those. So the first one that I'm going to do is the facing direction because that one is just a little bit simpler. So it's kind of easy to explain how these material property overrides work. So we're going to need to implement this on the character authoring because we want both our player characters and enemy characters to be facing in the same direction that they're moving. So under character move speed, I'm going to go ahead and create a new public struct for the facing direction override. And this is an iComponent data. And in here, we'll just have a single public float called value. Now we're not quite done yet because we do need to add an attribute above here, and this is going to be the material property attribute. And we actually do not have this because we do need the using unity.rendering namespace. So once we have material property, you see we still have a red line under it, and that's because we need to specify the actual material property that we would like to modify. And you'll remember that we do have to use the reference string, and this is the reference string of the facing direction, which is underscore facing direction. And so you remember with the facing direction, when that value is 1, we're facing to the right, and then when that value is -1, we're facing to the left. So let's go ahead and add this to the character. So inside the baker for this character, say add component, and we'll add it to the entity for the new facing direction override. And here we can just set a default value of equal to 1, because if we don't have a default value, then the facing direction is going to be all wrong. And I don't even think the character displays actually. So we'll set a character override with a default value of 1. And then if we enter play mode, you see that our character is still playing with their animation. If we select player and let's go to the runtime data, and we'll scroll down to the facing direction stuff. So we have facing direction override. So now if we set this to a value of -1, you'll see that he's now facing to the left, and 1 is to the right, and 0 is nothing. But so yeah, we're just basically gonna be changing this between 1 and -1, depending on which way we want this character to face, which is based off of whichever way that they're moving. And so we can actually go into our character move system, and we can also just kind of handle this stuff inside of here because it is a fairly decent enough place to actually do that. So this isn't actually a requirement, but I typically like to order things in my for each query with ones that we need read-write access to first, followed by ones that only need read-only access. Again, order doesn't matter. You can have them in any order that you want. This is just kind of a personal preference. So I'm going to do a ref RW on the facing direction override, and then we just need to add this to the tuple. So after velocity, we can say facing direction. And then now we can actually write to the facing direction. Now we don't actually want the facing direction to be updated every frame, because again, if the character is not moving, we don't want that facing direction to be set to 0. So what I just end up doing is I say if math.abs for absolute. So we take the absolute value of the move step 2d.x. So if that is greater than 0.15, then we can actually go ahead and set the facing direction just again by accessing the value rw.value. And we can set this to the math.sign, and that's SIGN sign, passing in the move step 2d.x. So the idea here is if move step 2d is a negative number, this math.sign returns a -1. If move step 2d.x is a positive number, math.sign returns a positive value, and we just set the facing direction. And then again, because we're checking to see if the absolute value is greater than this number, then that means that we actually need to be moving for it to change the direction. Whereas if we're just stationary, we still want it to just keep the same direction that it previously was facing. Okay, so let's enter play mode, and you can see that we can move our character up and down, and they're still just staying in the same direction because again, we're just looking at the X direction. If we move to the right, we're still staying right. Okay, very good. And let's go to the left, and boom, we're going to the left. So now if we go up and down, we're still facing to the left. If we stop, we're facing to the left. We can flip back over to the right and left, and then, yeah, this is exciting stuff, right? So yeah, if we're moving at diagonal angles in one direction, it's going to just go in that correct direction. So again, it's kind of the X direction, whatever it's facing, it's going to be facing in that direction. So yeah, that's cool stuff, man. Now, what's not cool stuff though is we're still walking in place. Again, we want our idle animation to play when we're just walking in place. Now this one's going to be a player specific one because only the players again have idle and walking animations, whereas the enemies only have walking animations. So there's going to be a couple things in order to get this to work. So one, we're still going to need a material property override so we can override the animation index that's currently playing. And number two, I'm just going to create a nice little helper enum for us that allows us to easily switch between the correct animations without having to remember the index each time. And then three, we're going to need a way to determine if the character is moving or stopped. So over in player authoring, I'm just going to create a couple of these things that we need here. So one, we're going to need the public struct for the actual animation index override. And this should actually be an iComponent data. We do need to include the material property attribute on here. And the reference string is underscore animation index. And here, same as before, we do have a public float called value. And then let's go ahead and create our little helper enum. So this is a public enum for the player animation index. And this can just be a byte enum, and we'll set movement equal to 0, idle equal to 1, and we'll just say none equal to byte dot max value. So again, the animation indexes, they kind of start at the bottom of the sprite sheet. So movement is the first one, so that's the 0 index, and then idle is the one above, so that's kind of the 1 index there. And then so we're just going to use this little helper enum for us to set the animation index. And then the last thing that we need to do is just scroll down to here, and on the player, do an add component. We're going to go ahead and add that animation index override to that entity. So we can also do this inside the character move system. So I'm going to show you another little handy thing that we can do sometimes. And actually I'm doing this slightly different in .survivors. Like I think I have a specific system that checks the previous player's input with their current player input and sets the animations appropriately. But in this case, I think it's totally fine for us to just continually set the animation index here. So let's go ahead and do another if check here. So we'll say if system API, using our nice handy system API again, dot has component player tag, because again, we want these to only apply to the players. Power to the players. Now we do need to pass in the entity here. So let's go back up to the for each and say dot with entity access, and then we need to add on entity to the tuple. And so basically we're saying if this entity has the player tag, let's say var animation override is equal to system API dot get component RW animation index override. Of course, get that from the entity. So what's happening here is we are using system API to get this animation index override component from this entity. Now there is just a regular get component method, and this works totally fine. But the RW method is a nice handy one because this allows us to actually write to this component without having to like set back to it with an entity command buffer or entity manager or something like that. So it kind of gives us a similar ref RW variable type and allows us to just modify it directly. So here we can actually just go ahead and say like animation override dot value RW dot value is equal to 1. And so this is just going to force it to be in the idle animation. So now when we enter play mode, you'll see that our player is now playing the idle animation. So now we want to actually determine which animation to play based off of the character's current movement state. So let's go ahead and say var animation type is equal to, and we can figure this out by looking at the move vector and basically see that if the character is moving. So we can do this by saying math.length SQ for length squared, and we can just pass in the move step 2D, and this gives us the essentially length of the vector. So if the character is not moving, the length is going to be 0. If they are moving, then the length is going to be some, number greater than 0. And we're using length s squared as a little bit of an optimization because it's more efficient of calculating the length of something, and we can just say if this is greater than float.epsilon, which is just a very small non-zero number. So basically it means, if we're greater than that, we know that we're moving. So we can use the little ternary operator here. So say question mark. And the first thing that we would want to apply is the player animation index dot movement. And again, the reason for that is, if the move length is greater than a small number, we know that we're moving. Otherwise, we can set player animation index to idle. And so once we have our animation type, then we can actually assign that to the value here. We do need to cast that to a float, that animation type right there. And then so now, basically again, when the player's moving, the player's move animation index will be set. And then when they're not moving, the idle animation will be set. So we'll go ahead and enter play mode, and you see that we have the idle animation playing, and let's go ahead and start moving, and you see that the character's walking animation is playing. And so now, again, the walking animation and move direction are all set up correctly, and if we stop moving, it'll transition right over to the idle animation. So that's exactly what wants to happen. We have these nice transitions between the idle and moving animations, again, all based off of shader properties, which are accessed through ECS, which is super, super cool. By the way, if you are enjoying this tutorial so far, I do just want to remind you that you can find a whole lot more just like this over on the Unity Asset Store, where I have the complete project files and documentation of my game Dot Survivors available for purchase. And this documentation includes written and video overviews of a few dozen of the most important concepts of the game, so you can learn more about creating a fully scoped project rather than just a simple little tutorial tech demo like this, but learn how some of these concepts fit into a game where we actually need to account for the scale of things and implement some interesting workarounds in order to get things working properly with Unity. I put so much into this project to make it as good as it can be, and I really think that it's going to be an excellent learning resource for anyone who wants to make a full game with dots and ECS. So check it out if you want, but if you're not interested, a like and subscribe on this video is helpful too. Okay, great. So we can move our character around the screen. Now let's actually add a little bit of a gameplay into this supposedly game. So let's start adding in some enemies, and these enemies are going to chase down the player and deal damage when they come in contact with the player. So let's go ahead and go over to the moon entity scene, and I'm just going to go ahead and do the same old create game object, 3D object, quad, because again, this is going to be very similar to the player, and we can just call this alien or alien. So anyways, we're going to go over to the authoring mode and go ahead and remove that mesh collider for now. On the mesh renderer, we will add the alien material. This works very similar to the regular character material. We can actually go over to this alien material here, and you can see that it's set up pretty similar to the astronaut. We just have the alien sprite sheet. Sorry again for the flashbang, but it just looks a little better with the white background. You can see that here's the aliens sprite sheet right here, and again, it just has that one single walking animation because the aliens are just going to be constantly moving. They're not ever going to be standing at idle. And then differences here is animation count is just set to 1, and that's because we just don't have multiple animations, and still running at 12 frames a second, frame count of 8 frames total. So fairly similar setup overall. Anyways, let's go over to this alien. I'm going to bump up the scale on this to 1.5 on each axis. And let's get in nice and close to this alien right here and add a box collider, and we'll go ahead and scale this down to roughly match the size of the alien itself right here, and then we'll just make sure and put a thickness of 0.15 on there. We'll go ahead and assign the alien to the enemy layer. So great, now we have our little alien set up. Now let's go ahead and actually apply some logic to this alien to actually follow around the character. So you'll recall that in our character authoring, we just have this one central character move system. And the intention here is to be able to move both player characters as well as enemy characters. Now, where it comes to be a little bit of split is where we're actually writing to this character move direction. So you'll remember for the player, we have the player input system where we're writing to the player's current inputs. So let's do some stuff specific to the enemy, and we're going to create a system to essentially find the player and set its move direction based off of the direction to the player. So over here, I'm going to go ahead and create a new C# class, and this will be the enemy authoring. And on here, we'll say using Unity engine and using Unity.entities, because I know that we're going to need both of those. So let's go ahead and create a public struct enemy tag to be able to identify enemies. Of course, this is an iComponent data with no values on it. And then on the enemy authoring, we'll make sure this is a mono behavior. And let's go ahead and just assign this enemy tag to the enemy via a baker. So do a private class baker. So we'll get a reference to that entity here by doing a get entity, passing in the transform usage flags.dynamic, and say add component of enemy tag to that entity. Now, a cool thing that we can do is that above this authoring component, we can create an attribute, which we say require component type of character authoring. So of course, these authoring components, they're all regular Unity mono behaviors, and regular Unity has this require component attribute, which means that if you add a mono behavior component to a particular game object, then it will require the existence of another mono behavior type. The cool thing about this is that if you were to say add the enemy authoring to the enemy game object, then it's also going to automatically include that character authoring mono behavior as well. And that's again because the design of our game, we need some things that are specific to the enemy, but also we need some things that are shared by both enemies and players, which we kind of put under this sort of character umbrella. So let's go over to the alien and we'll say add component, and we'll just go ahead and add the enemy authoring. And you see when we add the enemy authoring, it also automatically adds this character authoring where we can define a move speed. Now let's go ahead and let's see, the player's move speed is 3.5. Let's go ahead and set the character's move speed to be 2.5. So they'll be a little bit slower than the player, which is nice. So now this kind of gives the alien enemy the base ability to move around. However, again, we're still not setting anything for that character move direction. So let's go ahead and take care of that now. And one thing that I also forgot is we do need to add a rigid body component on here. We can say set the mass to like 10. Linear and angular dampening are set to INF infinity, and we do not want to use gravity. And let's go ahead and set the interpolation mode to extrapolate to smooth out the enemy's movement. In the main kind of dot survivors project I was working on, I did have this set to interpolate for the enemy characters, but I did notice this weird bug where when I was randomly spawning them, they would sometimes occasionally just like spawn on the screen, even though I was spawning them off screen. They would spawn at like random places on the screen. It was really weird. But when I changed it over to use the extrapolate, where it's not adding that additional buffer component, then the movement seems to be smooth and it's not spawning them all over. So anyways, weird little quirk there. So below the authoring, we'll create a new public partial struct called enemy move to player system, and it's going to be an iSystem. And then in here we can do a public void on update ref system state. And then, so first thing that we want to do is actually get the position of the player so we know how to actually move towards the player. So typically this would be where we might create, say, an idiomatic for each and be able to move towards the player. However, I'm going to do something a little bit different, and I'm going to use a job. And the reason that I want to use a job here is because the intention for this particular data transformation is that we're going to be running this across all enemies in the game every single frame. And we want to be kind of as efficient as possible when we get to the later stages of the game where we might have very, very large numbers of enemies. We kind of want to optimize for that case. So by using the job system, this is going to allow us to create a job where we can actually have all the enemies calculate their direction to the player that they need to move in parallel to each other on different job threads. So this is a very nice, handy feature to have. And so I'm going to just kind of demonstrate how we actually do that here. So even though we already have this enemy move to player system, we're actually going to be creating a separate struct outside of here. And then we're going to use that system to schedule this job. So this also is going to be a public partial struct. And this time we're going to call this the enemy move to player job. And rather than this being an iSystem or something like that, we're actually going to use an iJob entity. Now, an iJob entity, you'll see that there's a little red line under here, and that's because we need to have a private void called execute. And this execute method is where we're actually going to, execute the work that we need to. So what we're doing here is rather than in a for each where we create an entity query, we can use an implicit query as part of the iJob entity to find entities that match a certain query. So ultimately, what are we trying to do with this job? Well, we want to write to the character move direction, and we can just call this direction. And we also need to know the current position of the enemy. So in that case, we can get that from the local transform, and we can just call this transform. You'll see that we have a little red line under here because we need the unity.transform namespace. Now, a couple things that we need to do here, again, very similar to a regular idiomatic for each, we need to specify when we're reading from and writing to these different component types. So before character move direction, we just use the ref keyword, and that specifies that we're able to read from as well as write to the character move direction. And then also for local transform, we need to put in front of it. And that basically means that we're just reading from that local transform. And the final piece that we're going to need is the actual position of the player. So we can do a public float to, and of course, just import unity.mathematics. And we call this player position. So the reason we can have player position outside of here like this is because this player position is going to be the same for every single enemy that we're iterating across. Now, inside the execute, when we're kind of like defining these parameters here, these ones are going to map to individual values for individual enemies. And then inside the execute, we can actually do the work that we need to. So first we need to figure out the vector to the player, and we can get this from the player position minus the transform dot position. So that's the position of the enemy character. Now you see that we do have a red line under here, and that's because player position is 2D, whereas the transform position is 3D. So luckily we can just do a transform.position.xy, and that essentially just returns the X and Y components as a float too. And then we can do that subtraction. So now we have the vector to the player. And then here we can set the direction dot value. And because we're using the ref keyword like this and not like an enabled ref RW, we don't need to do the whole dot value RW thing. We can just set the value directly. And we want to set this equal to the vector to player, but that's not quite it, because the vector to player, it's going to be, it's going to be a bigger value if it's further away, which is going to make the character move faster towards the player, which we don't exactly want. So really we just want to do a math.normalize on here to make this vector a factor of 1, so that this is like literally just the direction to the player. And then again, their move speed is going to be able to scale that vector out to determine the actual speed. And one more thing that we can do on this job is above it, we can put the burst compile attribute, and make sure to import unity.burst. And the idea here is that this is going to be compiled using the burst compiler. So now this actually isn't going to do anything because we haven't scheduled the job yet. So let's go ahead and schedule the job. So let's go ahead and say var move to player job is equal to a new enemy move to player job. Now, we can do this just fine. However, we do need to set this player position so we know, actually where to move these enemies towards. So in here, we can kind of do one of these initialization types and set the player position equal to, for now, let's just go ahead and set this to float2.0, and we can just test out the player movement. And then after that, we can actually set it to be the actual player's position. So this is just creating the job struct. Now we actually have to schedule it. And so we can do this in a couple of ways. So we can say move to player job dot run, just like this. And when we do a move to player job dot run, that means it's going to immediately execute this job on the main thread. Now that's not exactly what we want, because that's pretty much the same thing as doing an idiomatic for each. So there's not really much of an advantage of using this .run rather than an idiomatic for each. We also do have the ability to do a .schedule, and a schedule means that we're going to schedule this work to run on a worker thread, but it's only going to run on one single worker thread. And then the final one we can do is a .schedule parallel. And the idea behind this one is that if we have a bunch of enemies, it's going to be able to run this job on multiple worker threads across, kind of all the available worker threads that we have. Now, there are some limits and caveats to how this actually works, but in general, when we have a very large number of entities and we're using a job like this, we typically want to aim for using the .schedule parallel. Now, doing this just like this works just fine. Like it kind of hooks into Unity's dependency system as we want it to. However, I just want to kind of be a little bit more explicit about it right now and just kind of display a little bit about what's happening under the hood. So this schedule parallel, it can actually take in an argument here for the state.dependency. And the state.dependency basically just means, hey, these are all the incoming dependencies that I have from any previous systems. So it kind of knows what other data components are being read from and written to. And so it basically allows us to tell this job to say, hey, we know which components we can safely access at a given time. And so that's great, but we also need to make sure that we are actually writing back to the dependency. So we can say state.dependency is equal to this job that we're scheduling here. So this says, hey, any dependencies that we're creating in this move job, let's assign those back to the state.dependency so that any further systems down the line, they can know about the dependencies from this job. Now, again, if we do just the move to player job.schedule parallel, how we initially had it, it should kind of implicitly do this for us. But again, it's just good, I think, to know kind of what's happening under the hood and how we can kind of be explicit about assigning the dependencies. And one thing that I actually forgot to do here is on the enemy move to player job, we only want this to update against any enemies. And there's nothing in our query specifying that, we're looking for only enemies. So actually there is a way that we can do this with another attribute. So we can say with all type of enemy tag. And so this means that anything that has the enemy tag, we're going to kind of add that as a requirement to this implicit query that's created with these component types right here. So anyways, we can come back to Unity and enter play mode here. You see that the alien will start moving towards basically just the center. And then when it gets there, it just kind of glitches out because it's moving back and forth. So its facing direction is always the same. And we can actually push them around and they'll basically just always move back towards that center position. So now let's go ahead and change things up a little bit so that the enemy actually just follows the player. So luckily that's pretty easy to do. So instead of just setting the player position equal to float2.0, we need to actually get a reference to the player's position. So instead of just setting it to float2.0, we'll actually get the player's position itself. So before getting the player's position, we actually need to get the player entity itself, and then from there we can get its position. So we can use our handy system API to do a .get singleton entity, and inside these type brackets we can look for the player tag. And so this basically means, hey, let's find the singleton entity that has the player tag component. So a singleton entity, all it really means is if we have a particular tag component that is only owned by one entity in the game, then that can be considered a singleton component, and then the get singleton entity just returns us that entity with that. Now, there's nothing like stopping us from adding player tag to multiple entities. So we can actually end up getting some errors where if we had like 3 entities tagged with player tag, we could no longer do get singleton entity because it doesn't know which one to return. Also, you will see that Writer is giving me this little yellow line under here. And if we just do the little Alt Enter to implement that, then you see that it creates our onCreate here. And then we do a state.require for update player tag. So we did use this require for update earlier. And this is just kind of it saying, hey, if you're doing this get singleton entity, well, you better make sure that that player tag actually exists. So, we'll make sure to do require for update player tag. And that way, if this player does not exist, then this update will not get ran because, we're looking for an entity that doesn't exist. So anyways, once we have the player entity, let's actually get the player position. And we can do this again by using this handy system API .get component. And let's get the local transform type here. And then inside, we do need to pass in the player entity because we want to say, hey, get the transform from this player. Now this actually returns the full local transform here. So actually what we want to do is get the dot position off that local transform. And in fact, we want the 2D version of this so we can do a dot position dot XY. So then this player position, if we hover over it, it should now be a float to player position. And then in here, instead of setting this to float 2.0, we'll just set this to the player position. Boom, exciting. So now when we enter play mode, you'll see that the enemy is following the player. And as we move around, the enemy will continue updating its position. And you see that, it's doing cool stuff. Like it's actually able to, change its facing direction and all that. So yeah, this is looking really good. And by the way, the enemies can still go through the little boulders, even though the players are unable to. That's just kind of a little bit of a game design thing. In Vampire Survivors, all the enemies can run right through all the environment elements. So I just figured, hey, let's stay true to the source material. And obviously it's not that hard to like add the collision layer or something like that, but it's just is kind of how the game plays, and I decided to keep that way. Okay, so while we're on the topic of doing things for the enemy, let's implement the ability for the enemy to attack the player. Now, to accomplish this, we're going to need to kind of implement some kind of underlying infrastructure for keeping track of damage. So first, let's go over to our character authoring, and we're going to add a few new data components. So we can just add these, say, below the facing direction override here. So let's have a public struct for the character's max hit points. And this is an iComponent data, and this will be a public int value because we're just going to do integer hit points here. And then we'll do a public struct for the character current hit points, also an iComponent data with a public int for value. Now the idea again of having this split between the max hit points and the current hit points is the max hit points is just going to stay the same throughout the duration of the application, whereas current hit points is going to be updating as it's taking damage and maybe even healing itself and any of that. But in this, we're just taking damage. So on our character authoring, let's go ahead and add a new public int field for hit points. And so these are going to be the amount of hit points that the character basically has. So we can do add component to the entity for a new character max hit points. And here we'll set value equal to authoring dot hit points and do the same add component on the entity for the new character current hit points. The value is also going to be authoring.hitpoints. So now we can come back to Unity, and on our alien, let's give it some amount of hit points. Let's give it, say, 10 hit points. And our player, we can have more hit points. We can have, say, 100 hit points. And then, again, these are going to be just the set to the current and maximum hit points for them. And so now we need a way to actually apply damage from one entity to another. Now, there's a lot of different ways that you can approach this, and the one that we're going to be using is kind of the damage buffer approach. And with the damage buffer approach, the idea is going to be that points of damage can be accumulated from several places throughout the frame. They could even be accumulated on separate threads. We're not going to be doing that in this video, but it still has the ability to. So we're kind of adding all these points of damage into a damage buffer, and then we have a specific system in the frame that is going to go through that damage buffer, and it's going to essentially apply all those hit points in the buffer to the current hit points. So rather than like having a bunch of systems that directly modify the current hit points, we can just have one system that handles dealing damage. The nice thing about having that one central system that like actually applies the damage is within that self-contained system, we can check to see if the character's health is below 0, and then we know to destroy the entity. Or we can also play some special damage effects, or just maybe handle different types of situations for different types of damage. So there's a lot of things that we can do with having a dedicated damage system. So it's a pretty good architectural approach in my opinion. So to actually create this damage buffer, we're gonna actually need another component type, and this is gonna be a new component type. So we'll call this public struct, and I'll say damage this frame is what I like to call it. And this is an iBuffer element data. So by adding an iBuffer element data buffer to an entity, this is kind of the concept known as a dynamic buffer. A dynamic buffer is a way to associate array-like data with a specific entity. And in this case, we're going to be adding points of damage in this buffer. We're kind of accumulating them in this buffer, and then again, applying that damage to the character. So in the damage this frame actual component here, we'll have one public int field for value. And again, this is going to be essentially points of damage that are added to the character when we want to damage them. To actually add this dynamic buffer, we can use the add buffer and then just add in the type, which is the damage this frame. And then we can add this, of course, to the entity. By the way, if we have a dynamic buffer that we want to pre-populate with data, this actually returns a value here. And then so we can say, like ASDF at 0 equals new damage this frame, yada, yada, yada. So we can actually, populate this dynamic buffer inside the authoring component if we wanted to. But again, we're not starting with any damage. So now let's actually create a system where we can kind of accumulate these points of damage and apply them to the character's current hit points. So let's scroll just down to the bottom here below our global time update system, and I'll create a new public partial struct for the process damage this frame system, which also is an iSystem. So the idea here is that inside our onUpdate, that we're going through this buffer and applying these points of damage towards the current hit points. So here we can do just a regular for each. I'll put a little placeholder here in system API.query. And then again, in this case, we're going to be writing to the character current hit points. And we also do need access to the dynamic buffer of that damage this frame type. So basically what we're doing here is we need to write to this current hit points, and then to get access to this damage this frame buffer, we say dynamic buffer of type damage this frame. So now we can go here and just change this to hit points and damage this frame. So what we'll do first is we'll say if damage this frame. And if we actually hover over this is actually the dynamic buffer damage this frame. And so the dynamic buffer, it allows us to check to see if it is empty. So if it is empty, just go ahead and continue because we don't need to do any further damage processing on this particular entity. Otherwise, we're just going to go ahead and do another for each. And so this time we're going to say for each damage in damage this frame, we're going to go ahead and accumulate these points of damage against our hit points. So we'll say hit points.value rw.value minus equals damage.value. So again, this damage type, what we're calling right here, this essentially represents one element of this damage this frame type. And then so by saying damage.value, we're actually getting that underlying integer value for the damage to apply. So again, we're just kind of subtracting our hit points by that damage, and then what we want to do is just say damage this frame dot clear. And then that's just going to clear out the damage buffer so we're not, continually applying damage. And then so we're going to be adding one other thing to this system later on when it relates to actually destroying entities. But for now, this is enough to test. And let's just go ahead and add the burst compile attribute on here as well. Okay, so let's enter play mode. And this is actually only going to work if I pause the game because remember, we're clearing out that damage buffer every frame. And so it's not going to give us enough time to test adding a point of damage inside this damage buffer here to actually confirm that it's working. So first of all, I do want to point out that the character's current hit points and max hit points are both set to 100, and we can see this dynamic buffer of damage this frame here. So we can expand out this buffer and say add element, and we can add element 0, and we'll say add 5 points of damage. So I will go ahead and resume execution and pause again. So you'll see that the damage buffer cleared out. And if we go up to our maximum or our current hit points, the value is now down to 95, whereas max hit points were not changing, so it's still at 100. Now we can also go back to this dynamic buffer. We can add an element here. So we can say add 5 points of damage, and let's add another element of 10 points of damage. So this should damage for a total of 15 points this frame. So I'm just going to go ahead and play and pause and go back here. And you see that both of those points of damage have now been accounted for, and the character is now down to 80 hit points. So next up, I think the next logical thing would be to have the enemies apply points of damage to the character. And so we're going to do that by using collision events. And now collision events are a kind of Unity ECS specific concept where anytime two colliders, and at least one of them needs to have a rigid body, similar to just regular collisions in Unity, that when those two objects collide, for every frame of them being overlapped, we're actually going to raise what is known as a collision event. And this collision event, we can basically inspect this collision event and determine which entities this collision event is in between. And if this collision event is between a player and an enemy, well, we're going to have the enemy apply points of damage to the player. So actually, to get this to work in the regular Unity authoring components, we need to go onto the alien and make sure we go to our box collider, and we'll have is trigger unchecked because we want it to be a physical collider, not just a trigger. But the provides contacts, we do need to check mark that. It is a little bit weird, the wording of it inside the kind of Unity's custom physics authoring components through that samples tab. There actually is a little bit of a drop down where you can say collide raise collision events. And so that's the same as what this configuration is, where we have the is trigger not checked and provides contacts checked. That means it's going to properly raise collision events when this entity intersects with another collider. So I'm going to go ahead and add in two additional data components here. So the first one is a public struct for the enemy attack data. And this is just a regular iComponent data. And we're going to have two fields on here. So the first is going to be a public integer for hit points. So this is how many hit points of damage it's going to be dealing when it collides with the player. And then we also want a public float for cooldown time. And again, because these collision events are constantly being raised as the player and character are colliding with each other, we don't want to apply points of damage every single frame, or, even if it was dealing 1 hit point, it would like vaporize the player in like 1 second of collision, which is not exactly the best gameplay that we want. So this cooldown time is going to allow us to have a little bit of time between the enemy dealing out attacks. Now, how I've chosen to make this cooldown time work is we actually have another component on here, which is the enemy cooldown expiration timestamp. And so this also is an iComponent data, but it is also an enableable component. And in here, we're going to store a public double called value. Now you may remember that the elapsed time that we get from Unity is a double. So we're going to store this expiration timestamp as a double. The idea here is that with this component, when an enemy goes on cooldown, that will set the value of this equal to the current game time plus the cooldown time to get the time that the cooldown essentially expires. And I've also chosen to use this as an enableable component, so we can have a specific portion of our enemy attack system look for anything with this cooldown expiration timestamp and enable it or disable it. And then basically, if this is enabled, it means the enemy is on cooldown and it's not able to attack. But if it's disabled, it's not on cooldown and it is able to attack. So let's just go ahead and add this enemy data here. So in the enemy authoring, we're gonna need 2 new fields here for the public int, let's say attack damage here, and then public float for cooldown time. And so we'll go ahead and do an add component on the entity for a new enemy attack data. And by the way, this is kind of one of the naming conventions that I typically like to use, where if a data component requires multiple fields, I'll typically end the type name with the word data. So then we'll actually assign the data. So hit points is equal to authoring dot attack damage, and then the cooldown time is equal to authoring dot cooldown time. And then we also need to make sure that we're adding in the component for the enemy cooldown expiration timestamp, of course adding that to the entity. And then we don't want our entity to be on cooldown by default. So what we can actually do is we can say set component enabled, passing in the enemy cooldown expiration timestamp. And so by default, when we add this component to the entity, it's going to be enabled by default. And we want it to start out as disabled because we don't necessarily want the enemy to spawn with the cooldown enabled. Even though the cooldown time is relatively short, but still it's nice to show this handy little API where we can say set component enabled, and we pass in the component type, which of course is the enemy cooldown expiration timestamp. So we have to specify the entity, and we can pass in true or false if we want it to be enabled or disabled. So we'll set it to false for disabled, and then again, it'll spawn being disabled. So anyways, moving down below the enemy move to player job, let's go ahead and create a public partial struct for the enemy attack system, and this is an iSystem. So here we'll go ahead and do our on update, public void on update, ref system state. And so first thing we'll do is we'll check to see if the entity is on cooldown. We'll see if its expiration timestamp has elapsed. So we'll go ahead and do a for each here, little placeholder in system API.query. And so we'll look for anything that has that enemy cooldown expiration timestamp. And we're also going to do that enabled ref RW against the enemy cooldown expiration timestamp. So the purpose of having this kind of twice in there is this one, it allows us to actually access the underlying data so we can actually see what the cooldown expiration timestamp is. And then this enabled ref RW of this allows us to set the enabled disabled property. Now, having both of these things in here like this means that this component does need to be enabled. So this system is only going to run on entities that are currently on cooldown. If the entity is not on cooldown, this system will not run for them. So let's go ahead and just change this here. So we can just call this the expiration timestamp, and then we'll say cooldown enabled for the enabled ref RW. So now we need to check what the current elapsed time is, and we can get that from system API.time.elapsed time. So let's say if the expiration timestamp.value is greater than the current elapsed time, so meaning that the expiration timestamp is still further off in the future, just go ahead and say continue. And then we'll continue to the next iteration. Now, if this check returns false, where the elapsed time is greater than the expiration timestamp, then we know that it should be off cooldown. So we'll go ahead and say cooldown enabled.value RW equals false. And then so cooldown will be disabled, and then that entity will no longer be iterating in this part of the for each loop here. So again, this is just us kind of like figuring out if the entity should be on cooldown or not. And now what we'd like to do is apply damage to the player when the enemy comes in contact with the player. Now, like I mentioned, Unity ECS has this concept of collision events. And so what we're going to be doing right now is actually scheduling a job to react to these collision events. So outside of the attack system here, we'll do another public struct. This does not need to be a partial struct, and we can call this the enemy attack job. And this is going to be a special job type of iCollision events job, and make sure that that is actually a plural collision events. And so this actually does require the Unity physics namespace, and you'll see we have a little underline under here because we need to implement the specific missing members. In this case, it's this public void called execute, which takes in a collision event, and we have access to it via this collision event. Now, the first thing that we need to do in our collision event is we need to make a determination, because inside this collision event, we have two entities. There's entity A and entity B. And we don't know anything about entity A or entity B. We just know that it's two entities that are part of this collision event. That means they're colliding, actively colliding with each other on this frame. So what we need to do is we need to figure out which one of these entities is the player and which one of these is the enemy. And also confirm that this collision event is actually between an enemy and a player. And it's not like, collision between two enemies, or it's not a collision between the player and an environment rock. So we're going to kind of take care of both of those things at once. Now, the way that we do that is, unfortunately, we don't have access to our handy system API from inside of this job here. So when we're doing, these things like system API.get component, there's also a system API.has component where we can see if an entity has a particular component. So again, we can't use that here. So we have to do what system API is actually doing under the hood, and that is creating what is known as a component lookup. And that component lookup allows us to check to see if an entity has a component. If it does have a component, we can actually get the active values for that component. We can even set the values on that component. So it's kind of a nice thing to do, and it kind of goes a little level deeper than what Unity kind of hides away in some of the nice code generation stuff with System API. So we'll go ahead and define this as a public component lookup. So the first one that we want to do a lookup against is the player tag. So again, we have to figure out which of these entities is the player. So we can call this the player lookup. And one thing that we do need to do is before this, actually add the read-only attribute. You'll see that there are actually multiple types of read-only. And so we want to import the unity.collections read-only attribute. And so if we just go up to the top, you'll see that there is just using unity.collections. If you have that in there, then it should import the correct read-only type, because there's, again, multiple read-only types. And this read-only tag, again, it kind of feeds into some of the things I've hinted at a little bit about dependency checking, where, we can kind of provide some additional information to Unity's safety dependency checking to say, hey, we're only reading from this component. And let's do the same thing for the enemy. Rather than doing the enemy tag, we can actually kind of kill two birds with one stone here. And we'll say enemy attack data. And this enemy attack data is going to give us access to, how many points of attack damage we want to deal to the player. So in this case, we can call this, say, the attack data lookup. And so we'll just start with these. We're going to add a couple more in just a second here. But so again, the first thing we need to figure out is which entity is the player entity and which entity is the enemy entity. So we can do that by just a couple quick little if-else checks. So we can say if player lookup dot has component, passing in the collision event dot entity A. So this says, hey, if the entity A has that player tag that we can look up from the player lookup, then we kind of know that entity A is the player. But we also want to check to see if the attack data lookup dot has component the collision event dot entity B. And I just realized I'm doing should do a lowercase c collision event because it's the actual type that we're doing on here. So anyways, if this is the case, then we know that the player entity is equal to collision event entity A, and the enemy entity is the entity B from this collision event. And then, so we also kind of need to check the opposite case. So we can actually do an else if player lookup dot has component collision event dot entity B, and then attack data lookup has the entity A. Then again, this is now the opposite case where the player entity is entity B and the enemy entity is entity A. And then we can say else return. So again, what's happening here is we're just determining which entity is the player entity, which enemy is the enemy entity. And then this else return basically means that if the collision event is not between one player and one enemy, then it's a different collision that, maybe is valid somewhere else. But right now we're just looking for collisions between enemies and players so we can deal points of damage to the enemy. So at this point, we've kind of figured, hey, we know that the collision event is between a player and an enemy. Now let's actually deal some points of damage. And again, we don't want to constantly deal damage. We only want to deal damage when the enemy is not on cooldown. So how do we determine if the enemy is on cooldown or not? Well, you'll remember that we set this up as an enableable component, and anytime that this cooldown expiration timestamp value is enabled, then we know that it is on cooldown and it cannot attack. However, if it's disabled, it can attack. So what we can do is back in the enemy attack job, let's go ahead and add another public component lookup. And this one is going to be for the enemy cooldown expiration timestamp. And then we can just call this, say, the cooldown lookup. And you'll notice that I did not add the read-only attribute in front of it. And that's because when we actually apply an attack to an enemy, we're going to be setting a new value for this cooldown expiration. But we'll do that after we actually apply the damage. So anyways, after the whole if-else deals here, so we can do another if check here to say if cooldown lookup dot is component enabled and pass in our enemy entity, because again, we figured out who our enemy entity is from this step right above here. So again, we're basically just saying, is the component that have the lookup on, this enemy cooldown expiration, is this enabled? If it is on that enemy entity, let's go ahead and return, because the entity is on cooldown and we don't want to apply any damage. Now, if it's not on cooldown, let's actually apply some damage to the player. Before we actually apply the damage, let's just go ahead and reset the cooldown timer, because we're kind of dealing with that right now. So first we need to get the attack data. And remember, we already have the attack data lookup. So we can say attack data lookup. And the way that we actually get a particular component is we can actually kind of use the array indexers almost to pass in the entity. In this case, it's the enemy entity. And then that returns us the attack data from this attack data lookup. So what we're doing is we're saying, we have this whole data lookup here. We can pass in the entity to it, and then it's going to return the data component for that entity of that type. So you see this attack data is that enemy attack data type. And we can do something similar where we want to, say, set the data. Again, we're setting the data on this cooldown lookup. And so we're setting this for the enemy entity, and we can set this equal to a new enemy cooldown expiration timestamp. And here we can just directly set the value here equal to elapsed time, which we don't have yet, but we can get, plus the attack data dot cooldown time. And so anyways, we'll just define a field up here for the public double elapsed time. And then we can set this when we actually go to schedule the job. So anyways, let me just kind of recap what I'm doing right here. So first we're getting the attack data, and we know that from the attack data, we can get the cooldown time, how long it is between the next attack. And then we can actually set this cooldown expiration timestamp equal to the current game time plus that additional cooldown time. And the way we set that for that entity is by going to our cooldown lookup, indexing it by that entity itself, and we can directly set that data right there. And again, the reason that we can do this on this type is because we do not have the read-only attribute on here. For these read-only ones, we're only able to read data from these. We can't actually write data to these components. And again, that just kind of goes into the safety dependency checking that Unity does. Now, you will remember that there is actually one other thing that we need to do, and that is to enable this component. And so we can again use the cooldown lookup and do a .set component enabled. And then in here, we pass in the entity, which is the enemy entity. And then we pass in true or false for true if we want it enabled, false if we want it disabled. And we do want it set to true so that it does go on cooldown. So at this point, we're basically, when we collide with the player, we're just going on cooldown again, but we're not actually applying any damage. Now you'll remember that the way that we apply damage is not by directly modifying the current hit points component of the player. It's by adding points to that damage buffer. So let's go up to the top of the job struct and go ahead and create a new lookup here. This time it's actually going to be a buffer lookup, and that's because the damage, this frame, is a dynamic buffer. And so we can just call this the damage buffer lookup. And then scrolling back down here, we'll go ahead and just at the very bottom, and we'll say get the player damage buffer here. And so we can get this equal by grabbing the damage buffer lookup that we just created here and passing in the player entity. So once we have the damage buffer from the player, we can just say player damage buffer dot add, and this will add a new damage this frame. And the value of this is going to be equal to attack data, because remember we already grabbed the attack data from the enemy entity right here, dot hit points. And that is going to add a new point of damage to our player. So if we went over to Unity right now, it's not going to work. Why is that? Because we're not actually scheduling this job. So inside this enemy attack system, we're going to schedule this job. So below this for each, we can go ahead and say create a new, we can create a new attack job equal to new enemy attack job. And then here we have to set all these component and buffer lookups and the elapsed time and all that. So we can do that just all right in here. So we'll just go top to bottom. So we'll start with the player lookup. And we can get these, again, because we're back in our system, we can use our handy system API .get component lookup, and we pass in the type, and this is the player tag. And then inside the parentheses, we'll pass in true or false for is read only. Again, because we are doing read only on this, we'll go ahead and pass in true here. Next up, we'll get the attack data lookup. Also using our system API to do a get component lookup against that enemy attack data. And this also is read only, so we'll pass in true there. For the cooldown lookup, we get this by doing a system API.get component lookup for the enemy cooldown expiration timestamp. And this one, we can just leave that empty because it defaults to false. And the final lookup that we need is the damage buffer lookup. We can set this equal to system API.get buffer lookup this time. And in here, the type is damage this frame. And then is read only is false by default, and we do need to write to it, so we'll leave it blank like that. So anyways, actually we also do need to add in one more thing, which of course is the elapsed time. And we already did grab the elapsed time up here, so we can just do elapsed time like that. So once again, this is us just kind of creating the job struct. Now we actually need to schedule the job. And it's a little bit unique how we have to do this for these collision events jobs, because we need something known as the simulation singleton, which is part of Unity physics. So we'll say var simulation singleton is equal to system API.get singleton. And the type is just the simulation singleton like that. And then writer is going to give us a little warning because we should add the required for update on the simulation singleton, so we don't end up having like any null singletons or anything. So once we have the simulation singleton, now we can actually schedule the job. So again, I'm going to be really explicit and set the state.dependency equal to this new attack job dot schedule. In here, we can pass in the simulation singleton as well as the state.dependency, just like that. So the job has been scheduled. Let's go ahead and add just a couple more things here. So above this enemy attack job, we can add in the burst compile attribute on there. Also, when we're scheduling the job inside the on update, we can make this burst compiled as well. And one other kind of important thing is that above the enemy attack system, we need this to update in a very specific portion of the frame. So we'll say update in group, type of physics system group, and we do need to import the physics.systems namespace, and we do want this to update after the type of physics simulation group, but we do need this to also update before type of after physics system group. So the idea here is that this needs to update at this specific portion of the frame where we're inside the physics system group, but after this physics simulation group, because I believe that inside this physics simulation group is where all these collision events are effectively detected and raised. And we want to kind of run our own logic in the same frame that that collision event happened, but after it already happened for that frame. So having them after the physics simulation group will kind of ensure that that collision event has been properly raised and that we're able to kind of detect it in the proper spot in the frame. So anyways, I know that was a lot of code, but hopefully it was more or less straightforward. Let's go back to Unity and test it out. So when we're back in Unity, we need to make sure that we go to the enemy authoring, and let's say apply 5 points of damage, and we'll set this to a cooldown of 0.5 seconds. So every 0.5 seconds is going to apply 5 points of damage to the player. So I'll go ahead and click on the player, and I'm going to just have this set up in runtime mode so we can kind of enter play mode and immediately monitor those current hit points. And when the enemy collides with the player, you'll see that it's ticking down by 5 units every half a second about. And again, the idea with this is that we're adding to the player's damage buffer, and actually you can't see because we're kind of adding and clearing the buffer in the same frame. So it still says that the dynamic buffer has 0 elements in it. So that's not entirely accurate because it's adding and removing them in the same frame. And then it's using that buffer to actually decrement the hit points in here. Now, obviously we're way in the negative right now. So I think the next logical portion would be to actually implement entity destruction. Okay, so I'm just gonna go ahead and create a new script here, and we'll go ahead and make this a struct, and we can call this the destroy entity system. And we're gonna be using the destroy entity system for multiple things. So it's gonna be used for players, enemies, as well as the experience point gems, and some of the player attacks as well. So it's going to be used for kind of a lot of things in here. So this is going to be an iSystem type, and we do need to include the unity.entities namespace right here. And we do need to make this a public partial struct. And so actually, before we even do anything in the destroy entity system, I'm going to go ahead and create this public struct for the destroy entity flag. And so this is an iComponent data, but it's also an iEnableable component data. And the purpose of this destroy entity flag is this is going to be added to any entity that can be destroyed. And then we'll have it set to disabled by default. And then when we enable the component, then it basically means that this entity should be destroyed, and this destroy entity system will actually destroy that entity. Now, this kind of goes back into, the idea of having like one central system for things, because, there could be multiple places in code where we say destroy a particular entity. However, having this nice one central destruction system allows us to do some additional logic. Maybe we want to play a sound effect or spawn an item or some other things when the entity gets destroyed. So this kind of allows one place for all that logic to live. So I'll go ahead and do a public void on update here. And this does need ref system state. And so what we can do is just create a simple for each here in system API.query. And we're going to look for anything with that destroy entity flag. And we also do need with entity access as well, so we can actually destroy the entity. So let's go ahead and assign some names for these. Now, the destroy entity flag, it doesn't have any data, so we can just name this underscore because we're not even using it. But we still do need it part of the query right here. And then for the entity, we can just call this entity. Now, to actually go ahead and destroy the entity, again, we can't just say entity manager destroy entity right here, because that would be modifying with this for each iteration, and we would get some issues with that. So we do have to use an entity command buffer. I showed previously how to create our own entity command buffer. In this case, I'm going to show you how to use one of the built-in entity command buffers, because Unity has a couple of built-in entity command buffers that execute at specific points in the frame. And in this case, we can utilize these to destroy entity at the end of the frame. And so we'll get that with this end simulation entity command buffer system. This is I'm going to warn you ahead of time, this is a very verbose type name. So we can get this by system API.get singleton. And we have to type in the end simulation entity command buffer system.singleton. And then of course, writer is going to yell at us to say we should include the require for update, which we should. And so that just gets us the entity command buffer system. And then from that, we actually have to create the actual entity command buffer. And so we can do that by getting the end ECB system.create command buffer. And then in here, we have to pass in this world unmanaged variable, which you can get from state.world unmanaged. It's just required for creating those types of entity command buffers. Now, because this is a built-in entity command buffer, we don't need to actually manually call ecb.playback. Unity does that at that specific point in the frame, which happens, as you can imagine, at the end of the simulation system group. So in here, we can just say end ecb.destroy entity and pass in the entity. So right now, this is obviously a very simple system. We're just looking for anything with this destroy entity flag and then destroying it. However, a little bit later on, we're going to be adding some additional logic in here. Now there's a couple little cleanup things that I like to do here. We'll have this update at a specific portion of the frame here. So we'll say update in group type of simulation system group. Now I did mention that by default, when you create a system, it will spawn into the simulation system group if you don't specify it otherwise. But I do want to point this out because we can say order last equals true. And this basically means that it forces it to update at the end of that simulation system group. And again, because we are scheduling the destruction of entities inside this end simulation entity command buffer, let's make sure this actually updates before that end simulation entity command buffer system, because that's the system that actually plays back things that we're kind of recording in there. So anyways, we have this destroy entity system set up. Now let's actually go ahead and add this destroy entity flag to our characters. So back in our character authoring, we can just go to the character authoring, and down at the bottom, we'll do an add component, add that destroy entity flag, add that to the entity. And then again, we want this disabled by default, so we can do a set component enabled on the destroy entity flag entity false. So disabled by default. Now let's go to our good old process damage this frame system. And again, here's where we have a nice little method of checking to see if hit points dot value ro dot value. By the way, I don't think we've used this value ro yet, but it basically, when we have access to a component via this ref rw, we can say value ro, and that just gives us read-only access to it to basically just specify that we're not writing to it. So anyways, if the hit points dot value is below 0, then in here we can do a system API dot set component enabled the destroy entity flag on the entity to true. So we will disable it. Now we do actually need to get a reference to that entity. So at the end of our little for each here, with entity access, and then add the entity here. And actually, you might notice a slight little bit of a flaw with this kind of thinking here, where we're checking to see if the hit points are below 0, and then we're saying set component enabled destroy entity flag. Well, as of right now, there's not anything actually forcing this query to say, hey, this must have a destroy entity flag. So we would end up getting some errors if this system did happen to run on an entity that did not have this destroy entity flag. So we can kind of add that as a requirement here. Now you might be thinking, hey, we can just modify this query to say dot with all destroy entity flag. And that's like, oh, hey, we're saying, make sure that that entity flag exists on that entity. Unfortunately, yes, it does mean that, but it also means that that component must be enabled for this query to match. Luckily, there is a method that we can use instead, which is the with present. And this basically means that this entity must have the destroy entity flag, but it doesn't care whether it is enabled or disabled. So now let's come back to Unity. We'll enter play mode, and the enemy will come down towards the player. You see that hit points tick down, 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 down. And once it reaches 0, if all goes well, our player should get destroyed. Boom, there goes our player. Actually, I think I did notice one slight bug in our logic. We're checking to see if the value is less than 0, but really it should be less than or equal to 0. And then, so once again, we'll watch the character hit points tick down, 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 down. And then once it reaches 0, then this character, the player character, will be destroyed. So we no longer have a player character in the world, and the enemy just walks off into space. So now let's go ahead and start adding a little bit of additional logic to our destroy entity system. So early on, you will remember that we do have this game UI, and we do indeed have a game over panel on here. Luckily, I've kind of already thought about this, where we do indeed have a show game over UI, which just calls this show game over UI coroutine, which just sets this game over panel to active after 1.5 seconds. So let's go to the destroy entity system here. And what we can do is, before we schedule the destruction of this entity, we can say if system API.has component player tag entity. So if the entity has a player tag, aka if the entity is a player, you can say game UI controller dot instance dot show game over UI. And that's just because I have this game over UI set up as a singleton mono behavior right here. So now if we play the game and the enemy starts attacking the player, after a little bit, the player should get destroyed any second now. And then after 1.5 seconds, we show this game over screen, and then it should all be wired up where if we click the quit button, it returns us to the main menu, and then we can click play, and then it will return us to the actual game, and we can play around again. And so yeah, we have, a little bit of a game loop. We have a game over state, but we don't actually have the ability to fight back. So let's implement the ability for the player to actually fight back. All right, so we're gonna start over in Unity, and in the Moon Entity Scene, I'm just gonna do as we've done a few times before and create a new 3D quad. And this is going to be the Plasma Blast. So this Plasma Blast, we can go ahead and go back to the regular authoring view right here. And of course, we'll remove this mesh collider and actually go to the mesh renderer, and we'll add the Plasma Blast mesh. The Plasma Blast mesh or the Plasma Blast material, I should say, is just a regular unlit material that just kind of displays this little Plasma Blast sprite. So on here, let's go ahead and add a sphere collider. And the sphere collider is nice because this should basically just wrap right around this Plasma Blast. So I'm not even going to do any adjustments to that. That looks great. What we do need to do is we want to check mark the box for is trigger. Now, we're going to do something similar to how the enemy entities can deal damage to the player, except we're going to be using trigger events rather than collision events. The reason that I want to use collision events here is because I want these attacks to essentially be able to pass through the entities, but only deal damage to them one time. Now, I'm kind of setting things up this way, even though I'm not really fully utilizing it in this tutorial project, but in the full .survivors project, we can have attacks that have a lot more kind of modularity to them, where they can, deal damage to multiple entities and so on. And so it just makes sense to have these as a trigger so they can kind of pass through the other entities without hitting the enemy and then it, kind of registering as a collision in that case, because we don't necessarily want that to happen. And then one last thing that I do need to do is on the layer, make sure we change this to the player attack layer. And we of course just don't want this like Plasma Blast in the scene. We actually want to spawn instance of these. And we can do that by using the prefab workflow. So I'm actually going to go ahead and create a new folder here for prefabs. And in this prefab folder, let's just go ahead and drag this Plasma Blast, and we can delete the Plasma Blast out of the main scene here. So what it's going to happen is our player is now going to have a reference to this Plasma Blast, and then we're going to be able to spawn these into the world. So let's come back over to the IDE, and below this player animation index, we're going to go ahead and do something similar to the player, what we did for the enemy. So we'll do a public struct here, and we can call this the player attack data. And this is going to be an iComponent data. And then on here, rather than storing an integer for the hit points, we're going to store a public entity reference for the attack prefab. And then with this prefab on there, we can instantiate instances of it in the world. And then similar to the enemies, we're also going to have a public float for the cooldown time. And also we're going to do that same type of thing where we have a public struct for the player cooldown expiration timestamp, which is an iComponent data. And again, this is going to have a public double just called value. So let's go ahead and add both of these things to the player. Now, this is something that we actually haven't done yet, is by storing a prefab reference. And again, we're going to be authoring these prefabs through game objects. You saw that when we created that Plasma Blast prefab, we just dragged it into a prefabs folder like we would with any regular game object. So what we're actually going to do on the player authoring, we'll create a new field for a public game object for the attack prefab. And then basically inside our baker, we're going to, not only are we already doing the conversion for the player game object to the player entity, but we're also going to convert this attack prefab from a game object to an entity. And here we can also do a public float for the cooldown time. And so let's go ahead and add our components here. So we'll say add component to the entity. This is going to be the new player attack data. And on here, the attack prefab, we'll set this first. And so we can't just say, authoring.attack prefab, because that attack prefab from the authoring is a game object, and we need to store this as an entity. Now we can actually convert this in the same way that we're converting the player entity, just by doing a get entity. And then for the first argument for this, we can pass in the game object that we want. So we'll say authoring.attack prefab. And then the second argument, we still need to put the transform usage flag. So transform usage flags dot dynamic. And then that again is going to give that attack entity all the necessary transform components that we want. And then we can just set the cooldown time from the authoring.cooldown time as we would expect. So that's us setting the player attack data. And then we also just need to do an add component against the player cooldown expiration timestamp. And add that to the entity. And by the way, I should just point out a slight difference is I'm not setting this player cooldown expiration timestamp as an enableable component, just because I'm just going to check this value every time in the system, and that's totally fine for these players like this. So anyways, let's actually go about creating our player attack system. So below player input system, looks like we can go ahead and do a public partial struct for the player attack system. And we'll make this an I system and do a public void on update ref system state. And so here we'll define our for each var with a little placeholder in system API.query. So we're going to want to query for a couple things. The first one is we'll do a ref RW on that player cooldown expiration timestamp. And that's basically because in this system, we're just kind of controlling when the player is shooting out attacks, and it is all going to be self-contained in here. So we can check the timestamp, set the timestamp, do what we need to do. Next up, we will need that player attack data. So we know what prefab to spawn and what our cooldown time is. We also need to know where to actually spawn the attack prefab, and we can just get the local transform of the player right there. And that should be all that we need for the time being. And so let's go ahead and assign some names to these variables. So let's say expiration timestamp. For player attack data, we'd call this attack data, and transform for the transform. So first thing we can do is say if the expiration timestamp dot value ro dot value is greater than the elapsed time, then just go ahead and continue. And so that means we do need to figure out the elapsed time. System API.time.elapsed time. So next up, we can get the spawn position, and we can just get this from the transform.position, just like that. And then to actually spawn a new instance of this, we're going to need an entity command buffer. And typically when we're spawning things, we want to spawn things on the next frame. That's because there ends up being a little bit of a weird glitch where if we spawn them on the current frame, some particular things aren't going to be updated. So it will spawn, so it will like display the prefab at the origin position, even though we're like setting the position differently. There are multiple ways that you can work around this, but what I typically like to do is just spawn things at the beginning of the next frame. And then again, if we have any initialization logic, that can all take place before any other systems happen. So in order to spawn something on the next frame, we can actually use a special entity command buffer. And this is one of Unity's entity command buffers. So we have to get this by grabbing the ECB system. So again, we do a system API.get singleton. And this is the begin initialization entity command buffer system.singleton. And so this is kind of the entity command buffer that will update at the beginning of the next frame. And then next thing that we need to do is actually create the entity command buffer by saying ECB equals ECB system.create command buffer. And again, just pass in that state.world unmanaged. And then we could also create an onCreate method right here where we say state.require for update, begin initialization entity command buffer system.singleton, just to be extra sure that that exists in the world. So now to spawn the entity, let's go back into our for each, and we can use that entity command buffer that we just created and do an instantiate. And then in here, we can pass in the attack prefab that we want. And so we can get that from the attack data attack prefab. And so that will just kind of instantiate it off into the world. Now we need to actually set some data on it. And so to do that, we can actually get that new attack here just by getting that value off of that ECB instantiate. Now, this is actually not going to return the actual entity because you'll remember that entity command buffers is just us recording the operations. So at this point, the entity doesn't actually exist. We're just saying, hey, I want to instantiate this, but that instantiation hasn't actually happened yet. Now, this value that we get returned, this technically is an entity type, but it's going to be an invalid entity because it uses just kind of like essentially a temporary index. So the entity command buffer can still do operations with it, but it's not the actual like entity index. So that's just, something to keep in mind where if you're like storing references to entities, you actually can't get it from this ECB instantiate. But in this case, it doesn't matter because we just need to set some data on it. So we can do an ECB.setComponent. And in here, we pass in that entity, which is the new attack. And then we want to set its local transforms. So we can actually just say local transform dot from position, and then pass in the spawn position. And that will create a local transform component, setting it at the spawn position, setting its orientation to quaternion.identity, and its scale to 1 by 1 by 1. So that will just spawn the entity in the world. And then the last thing that we want to do is just set the expiration timestamp for the player. So we can just set this to value rw.value is equal to the current elapsed time, which we already have. We can just set this equal to the current elapsed time, which we already have, and then add in the cooldown time, which we also get from the attack data. So this will just effectively reset that timestamp. So the next time it comes around, then this timestamp will be off into the future. And then, we'll kind of basically skip over that until the expiration timestamp is up, at which time we can spawn a new attack. So back over in Unity, we can go to the player and then we can assign this attack prefab. So we can just grab the Plasma Blast game object right there. And let's set this to a cooldown time of 1 second. So now let's go ahead and enter play mode here. And you can see as we move around, about every 1 second, it's going to spawn one of these plasma blasts just right where the player is. So let's just go ahead and stick with the player attack system for now. And what we're going to do is find the closest enemy to the player, and we're just going to be shooting an attack directly towards it. So the first thing that we need to do is kind of like figuring out this sort of like detection area of where we want to locate the enemies. In this case, what we can do is we'll take the spawn position and then we'll just add an offset in the XY axes. And we can use that as a sort of like detection box that we're locating these enemies in. And then once we have that whole list of enemies, then we can just iterate through that list of enemies and figure out which one is the closest to the player. So let's go back to the player attack data, and we're going to add an additional field in here. And this will be a public float3 for detection size. And so I'm actually just going to, in the player authoring, define a public float for detection size. And then I'm just going to go down here into the player attack data, and we'll set detection size equal to a new float3. And we can just pass in our single authoring dot detection size in there. And when we actually author it this way, where we just pass in a single float for this float3, it will assign X, Y, and Z all to that detection size. So then back in the player attack system here, then we can figure out the var min detect position is equal to the spawn position minus attack data dot detection size. And then we can do the same thing here, but define a max detect position. And in this case, we're going to be adding in the attack data detection size. So once we have these minimum and maximum positions, we're going to execute what is known as an overlap axis aligned bounding box. So this is going to create an axis aligned bounding box, and we're just going to say, hey, are we overlapping with any enemy entities? So the way we actually have to do this is create a var AABB input. And we'll set this equal to a new overlap AABB input. And so we actually do need unity.physics to get this overlap AABB input. And from here, we can define the AABB equal to a new AABB. The min position is going to be the min detect position. And then for max, this will be the max detect position. So when we define this overlap AABB input just like this, this is going to return us every single collider within that bounding box. Now, we don't exactly want that because we don't want to, return colliders for the player, any of the environment elements, any of the player attacks. In this case, all we care about is the enemies. So we can actually set a filter on here. We can set this equal to a filter, which we can actually just store inside this player attack data. So let's come back up to our player attack data, and we'll add a public collision filter and just call this collision filter. And then, so we actually have to set up this collision filter inside the authoring. So actually before we add this player attack data, we need to basically figure out the layer mask for the enemy. It's a little bit weird how we have to do this. It's kind of nice when we use Unity's custom authoring components because we can assign these values a lot easier through like different physics templates and things like that. But you'll remember that, we're using the regular Unity authoring and we're using these layers up here. So we need to, figure out the index of the layer, but then basically get the bit mask of the layer. So we're getting a unsigned integer with the bit at index 7 set for the enemy, because we only want to collide with enemies. So first thing we need to actually get is the enemy layer. And so we can do that with just the regular Unity layer mask dot name to layer. And in here, we can pass in the name of the layer, which is enemy. And so again, that just returns us, if we hover over this, this is just an integer. So this basically will just return us the number 7 because enemy is layer number 7. Now we need to essentially convert this to a bit mask, and we can just do this by doing a enemy layer mask equal to, it has to be an unsigned integer, so UINT, and then we can do math.pow to enemy layer. So this is basically just saying, 2 to the power of 7, and then that will return us the layer mask where the bit at index 7 is set to value 1. So then we can now actually create our collision filter. So we'll say var attack collision filter equal to a new collision filter. And then here we have to set what layer it belongs to and what layer it collides with. So for belongs to, this doesn't really matter so much. So we can just say uint.max value. So that's basically just setting the digit of 1 for every single thing in there. And then we want it to collide with, so collides with equals the enemy layer mask, which we have there. So this is kind of one of those things where it's a little bit of a disconnect between Unity's kind of traditional layer setup and how Unity ECS kind of exposes these layers and collisions to us under the hood. But it is ultimately not all that difficult to deal with. So anyways, once we have this attack collision filter, let's just go ahead and go back to this player attack data and assign our collision filter equal to that attack collision filter. Yay. Okay. So now we have the collision filter, so we can come back to here where we're setting up this overlap AABB input and then assign the filter equal to the attack data dot collision filter. And actually I just need to put a comma after that. So now this overlap AABB input defines an axis aligned bounding box with a minimum position and a maximum position, both in world space. And then the collision filter on that is only going to be enemies. So the idea is we're going to execute this overlap AABB using this as input, and it's going to return us a collection of all the enemies within that bounding box. So to actually execute this overlap AABB, we need the physics world singleton. So actually, I typically do this outside of the for each here. So we can say var physics world singleton is equal to system API dot get singleton. And again, as you can imagine, this is the physics world singleton. And writer, of course, will want us to add the require for update to ensure that that actually exists here. So now we can come back down here into our for each after we created the AABB input. And so we can just do a physics world singleton dot overlap AABB. And then in here, we can pass in the input, so AABB input. And then here is where we actually will get an output of the native list. You see this is a native list of integers for all hits. So we first actually need to define that here. So you can say var overlap hits equals new native list of integer. You'll see that we do need to require the unity.collections type for the native list. We do also have to specify the allocator. And again, we can use that nice rewindable allocator, which is the state.world update allocator. So once we have that defined, let's go ahead and say ref overlap hits. And the idea here is that it will run this overlap AABB and it will add all of the enemies to this overlap hits native list right here. Now you will notice that this native list is of type int. So all it really is an index. And then also using our physics world singleton, we can essentially look up into the physics world based off of this integer body index to get some information about it. We can actually get a reference to the entity, or in this case, all we really need to know is the position of the enemy so we can find the closest one. And so, actually, by the way, this overlap AABB, if we hover over this here, you'll see that this returns a bool. So what we can do is we can say, wrap this in an if statement here, and we'll say if not physics world singleton overlap AABB, meaning that this did not actually collide with anything. Just go ahead and say continue. And then that way, the attack doesn't actually get spawned if there's no enemies on screen. And then next time an enemy does come on screen, we don't need to wait for the cooldown to happen again, because we're not resetting the cooldown here. So this is just a way to say, early out if we didn't detect any enemies in this radius here. So now, again, we've kind of got the list of integers for all these physics bodies. Now let's say, hey, let's go through this list and let's find the closest one. So first, we can keep a reference to the max distance, SQ. I'm going to use the squared distances on here. So we'll set this to float.maxValue, and then we'll figure out the closest position, closest enemy position, and we'll just set this to float3.0 for default. And then here, let's go ahead and iterate through that list of overlap hits. So for each var overlap hit in overlap hits. So let's get the current enemy position that we're iterating over. So we can say var cur enemy position is equal to, let's go to that physics world singleton. And on here, we can say dot bodies, and then we'll pass in the index here. In this case, it's just the current overlap hit. And then once we have the body, we can say dot world from body.pos to actually get the position of that physics body in the world. So that's, again, the current enemy position. Now let's actually figure out the distance squared between that position and the player's position. So var distance to player SQ is equal to math.distance SQ. And so here we can just pass in the spawn position and the cur enemy position, and that will get the distance squared of that. Now there's a ever so slight optimization that we can do because we only care about the XY axes. We can just compare distance on the XY axes. Again, very, very slight optimization there. So anyways, once we have the distance to player squared, we can compare that distance to player SQ with the max distance SQ. So if the current distance is less than the max distance, we'll go ahead and set the new max distance equal to this current distance to player SQ, and we'll also save that position. So we'll set that closest enemy position equal to that cur enemy position. And then so we can save that. And then so, basically once this for each loop is complete, we'll know the position of the closest enemy, and then we'll fire the attack towards that. So how do we actually do that? Well, it's more math. I'm sure you guys love all this math. So anyways, we'll get the vector to the closest enemy. So say var vector to closest enemy. We can get that by the closest enemy position minus the spawn position. So this effectively gets us the vector from the player to that closest enemy. And so once we have that vector to closest enemy, let's figure out the actual angle to closest enemy. And we'll use the good old math.atan2 function. And here we can pass in the vector to closest enemy. First pass in the y, and then vector to closest enemy, and then pass in the x on that. So the atan2, this is kind of a fairly commonly used method in game development where we can pass in xy coordinates, and it's going to return us an angle in radians facing towards that vector. Definitely don't go overboard using this ATAN2 because from what I understand, it's a fairly expensive method to call. But if we're only running it once every half second or so, when we're determining a new enemy to fire towards and we're just doing it one time, this is not really that big of a deal. So when we have our angle to closest enemy, now let's actually get the spawn orientation. So to actually calculate the spawn orientation, we can do a quaternion dot Euler. Make sure this is the lowercase q quaternion because that's the nice burst compatible type. And so we're going to apply 0 in the X and the Y, and then pass in the angle to closest enemy right in there for the Z. And I should just, again, call out that when we do this lowercase q quaternion dot Euler, this takes in values in radians, and luckily this ATAN2 returns us this angle in radians, so we don't need to do any conversions or anything there. Okay, so once we have this spawn orientation, well, we need to apply this to the local transform of that new attack. Now, luckily, there's this nice little method that we can do here. So instead of doing local transform.from position, you can do a from position rotation. And then in here, we can pass in the second argument of the spawn orientation. And so with that, we should now spawn the attack facing towards the enemy. So we'll come back over to Unity and let's go ahead and increase this detection size to a value of 10. So this is basically going to make a, if you think about it, it's going to be 10 by 10 by 10 each direction offset. So really the box is going to be 20 by 20 by 20 that we're going to be looking at. And then, so let's go ahead and enter play mode here. And we can see that it is successfully detecting enemies because we shouldn't be spawning the actual attack prefabs if the enemy is not spawning. And it's going to be kind of hard to tell because this is a fairly circular attack type, but you can see that they're at different kind of angles. And so, again, it should be facing towards the enemy at all times. And let's actually see if we go get the enemy off screen here. We probably should stop. And yeah, you see that we do stop spawning those little attack prefabs. And then once the enemy is back on screen, we'll start spawning them again. So great. Everything is working good so far. So now that we actually are spawning these plasma blasts in the world facing towards the enemy, let's go ahead and actually move them towards the enemy now. This is actually going to be quite easy because we already have the orientation pointed towards the enemy. Now we just need to move them straight forward. Okay, so I'm going to go ahead and create a new C# script here. This is going to be a class, and I'll call this the Plasma Blast authoring because this is going to apply to our Plasma Blast. And we'll go ahead and add in the namespaces for Unity Engine and Unity.entities. And we'll make this Plasma Blast authoring a mono behavior. So now we're going to define some data. So this will be a public struct for the Plasma Blast data, which is going to be an iComponent data. And we'll have public float fields for the move speed and a public int field for the attack damage. So I'll go ahead and create a private class Baker Plasma Blast authoring. And actually we'll go ahead and add some public fields in here for the move speed and attack damage. And let's do our good old entity conversion by doing the get entity, passing in the transform usage flags.dynamic. And we can go ahead and add component to that entity, which is a new Plasma Blast data, and we'll define the move speed equal to authoring.move speed and attack damage for authoring.attack damage. So this adds kind of all the necessary components for moving and damaging. And so let's actually go ahead and create a system. And so this will be under here, and this will be a public partial struct for the move Plasma Blast system. And this is going to be an I system. And we'll do our public void on update in here, ref system state, and we can just do a regular for each here, and we'll do a little var placeholder in system API dot query. In this case, we want to move our plasma blast. So of course, we're going to be writing to a component, and we're going to be moving it by updating the local transform. Now, go ahead and import that. Now, it's totally okay in this case to update the local transform for these plasma blasts. So these take place in the physics simulation, but they're triggers. So it doesn't matter, like they're not going to hit a wall and they should stop at the wall. So, we're totally good with updating the local transform rather than updating the velocity component. And then we also do need to read from that plasma blast data here, and that is all we need there. So let's go ahead and give some names here for the transform, and we'll just call that data. That's totally fine, and it's going to be a very, very simple one. We of course do need a delta time from system API.time.delta time. And we'll set the transform.valueRW.position. And remember, we're going to be doing a plus equals here because we're going to take its current position and increment it by some amount. And what I've actually found is the proper thing we need to do to essentially get it to move towards the character is we can do a transform.valueRO.right. And this actually, interestingly enough, will move it towards the player. It's just kind of like how the orientation works of it, if it's spawning in a two-dimensional plane and all that. And then we can multiply this by data.moveSpeed, and of course multiply that by delta time. Okay, so we will come back over to Unity and select our Plasma Blast prefab, and we'll add a new component, which is going to be this Plasma Blast authoring. And here we can set a move speed, let's say a move speed of 7.5, nice and quick. And we'll have this deal say 4 points of damage. So actually take a couple of hits to destroy these enemies here. And so yeah, we can go ahead and enter play mode here. And you can see, boom, we're already moving immediately towards these enemies. So no matter what where they're at, it's always going to find the closest one and just shoot that plasma blast right towards it. Now, we're not dealing any damage to these. And again, we kind of have to create a little trigger system for that to actually deal the damage. So let's go ahead and take care of that now. So to actually deal the damage, I'm going to create a new system here. And this is going to be a public partial struct for the plasma blast attack system, which is another iSystem. And just a heads up, we are going to be scheduling another job. So we'll call this the public struct plasma blast attack job, which is an iTrigger events job. And so this iTrigger events job, this comes from unity.physics, and we can implement the member here. So again, this is going to be very similar to a collision events job, but it takes in this trigger event rather than collision event. So let's get to going on our job struct here, and then we can worry about scheduling it afterwards. So again, we need to figure out which entity is the plasma blast entity and which entity is the enemy entity. And so you'll remember that in order to get these, and sort of a nice little if-else here, is we have to get a bunch of component lookups. And so we'll do a couple of these read-only component lookups. Do need to make sure that we implement the Unity collections read-only type here. And we're gonna do a public component lookup. And let's get one for the plasma blast. We of course have the plasma blast data on there, and so we can call this the plasma blast lookup. And let's do one for the enemy as well, and this component lookup can just look up the enemy tag, and this can be our enemy lookup. And of course we do want to apply points of damage to the enemy, so let's do another public without the read-only attribute for the buffer lookup against the damage this frame. Yeah, damage this frame, and we call this the damage buffer lookup. And again, this damage this frame is applied to all characters, so the enemy already has this damage this frame. So anyways, let's figure out which is which. And so let's go ahead and say if plasma blast lookup dot has component passing in trigger event dot entity A, very similar to collision event, and the enemy lookup dot has component trigger event dot entity B. Then in that case, we know the plasma blast entity is the trigger event dot entity A, and the enemy entity is the trigger event dot entity B. So let's go ahead and copy pasta this. And then we'll change this to plasma blast is entity B, and enemy is entity A. And then we'll change this to B, change this to A, and then again say else return, meaning this trigger event is between something other than exactly one plasma blast and exactly one entity. And then here, all we need to really do is just apply points of damage to that enemy. So let's go ahead and say var attack damage is equal to the plasma blast lookup at the plasma blast entity dot attack damage. So that's, how many points of damage that we're actually going to deal. Again, just looking at that through this plasma blast lookup, which gives us the plasma blast data for that plasma blast. So we know how much damage to actually apply. Then we just also need the enemy damage buffer, and we can get that by the damage buffer lookup at enemy entity, and the enemy damage buffer, we can just add a new damage this frame, passing in the value equal to attack damage. So that again will kind of add a point of damage to the player. So let's go ahead and schedule this job. So back in our plasma blast attack system, can do our good old public void on update ref system state. So say var attack job is equal to a new plasma blast attack job. In here, we can get all of our buffer lookups. So we'll say plasma blast lookup equal to system API dot get component lookup, and we want to look up the plasma blast data. Next, for the enemy lookup, we'll get the system API dot get component lookup against the enemy tag. By the way, we do need to pass in true for is read only on both of these. For the damage buffer lookup, we can get this with system API dot get buffer lookup on the damage this frame, like that. And of course, once we have our attack job, we can schedule it by doing an attack job dot schedule. However, we do need to pass in that simulation singleton. So we can get that by saying var simulation singleton is equal to system API dot get singleton simulation singleton. And in here, we can pass in the simulation singleton. And I do also like to pass in the state.dependency and assign this back to the state.dependency as well. And let's just go ahead and require for update that simulation singleton. So that's us scheduling the job. And then, again, because this is a trigger events job, we do need to update this at the appropriate place in the frame to properly detect collision events for the frame. So say update in group type of physics system group, and we do need to import that type there. So we'll say update after type of physics simulation group, and then finally update before type of after physics system group. Boom. Okay, so now we can try it out. There's going to be one more thing that we need to do to finalize this. So we're going to go ahead and enter play mode, and this is actually going to be incorrect. I think it's going to be like kind of, blink and you miss it. The player or the enemy should get vaporized right away. Even though our attack damage is 4 and the alien has a hit points value of 10. So in theory, it should take 3 hits. But actually, I think it's going to take just 1. So let's go ahead and enter play mode and see what happens. So boom, and then boom, it just vaporized on the first one if you saw it. So I'll go ahead and play it again just so you don't miss it. And bink, he's gone. So anyways, good that we're applying damage, bad that we're seemingly applying too much damage. So do you know why that is? Well, that is because this plasma blast, we don't have any type of like cooldown on this plasma blast. And it would be kind of weird to apply cooldown to like an attack like in world like that. So what actually we're going to do is instead we're just going to go ahead and just destroy the plasma blast as soon as it hits the enemy entity. Because what's happening right now is every frame that plasma blast is colliding with that enemy, it's applying a new point of damage. So it really just takes 3 frames of overlap, which happens very quickly, to apply all the damage necessary to destroy that enemy. So all we need to do is actually pretty easy. We already have all the kind of infrastructure in place for this. So we'll go back to the plasma blast and we'll add the component of the destroy entity flag to this entity, and also make sure we say set component enabled destroy entity flag on the entity to false. So it's set to false by default. And then basically when we detect these trigger events, we can go ahead and enable that appropriate flag. So we'll do another public component lookup, and this one is going to be the destroy entity flag. So we call this the destroy entity lookup. And then so down at the bottom, after we're applying our damage, let's go ahead to that destroy entity lookup, and we can do a set component enabled on the plasma blast entity and set that to true. And by the way, why didn't anyone tell me I'm using capitals for these? I don't usually use capitals for those, so we can set those to lowercase for plasma blast and enemy entity. So yeah, anyways, we just need to go ahead and assign this component lookup. So back in the system here, and by the way, this cannot be a read only because we are actually changing the enabled state of it. Destroy entity lookup is equal to system API.get component lookup destroy entity flag. Okay, so now when we enter play mode, we should fire 3 shots until the entity finally gets destroyed. So that is exactly what we want, because the plasma blast is just getting destroyed right when it collides with the entity. So we're gonna move into spawning enemies next, but I do just want to provide a little bit of a challenge to you all. And that would be to also see if you can make those plasma blasts get destroyed after a certain number of seconds. Now, I will kind of include this in sort of the final code if you want to look up the solution to that, but I think you should have all the information that you need in order to create a plasma blast that will destroy itself after some certain duration. Hey, just wanted to cut in here and say, if you thought that attack is cool, then you might be interested in checking out the full project files over on the Unity Asset Store, where I have a total of 12 different unique attacks, each with their own level up progression system associated with them. And all of this is fully documented in the .survivors project files that you can purchase on that Unity Asset Store. Now, personally, I think this is one of the most interesting aspects of the game's architecture, but maybe you are interested in some other things yourself, like character stat modifications or dealing knockback or how to do more complex enemy spawn waves. And luckily I go into all that stuff and so much more in my project over on the Unity asset store called .survivors. So hope you check it out and learn a lot from it. Okay, so next up, we're going to basically turn this enemy into a prefab, and then we're going to create a spawner entity that can spawn a bunch of these enemies off screen, and then they're all going to, swarm the player, and it's going to be a grand old time. So let's go ahead and start off by doing just that. We'll grab this alien guy, bring him into the prefabs folder, and delete him out of the main scene. And I'll go ahead and right click on this moon entity scene. We'll create an empty game object, and this is going to be our enemy spawner. And so we'll just leave this as empty for now because it's really just going to be a data only entity. And if we come back over to here, we can create a new class, and this is going to be the enemy spawner authoring. So we do of course need the Unity engine and Unity.entities namespaces. So for this, we just need two data components. So one is going to be a public struct for the enemy spawn data. And this is going to be kind of the persistent data that's going to be relatively unchanging throughout the duration of the application. So first we'll need a public entity for the enemy prefab because we're just going to be spawning a bunch of these enemies. Let's also go ahead and define a public float for the spawn interval. So we want to, spawn one of these entities on a specific cadence. And let's also go ahead and create a public float for the spawn distance. The idea here is that we're going to basically just kind of like determine a random angle from the player, and then this spawn distance is just going to be enough to spawn that entity off screen at a certain distance away. The other data component that we're going to need is the public struct here for the enemy spawn state, and this is an iComponent data. And again, here's kind of the separation that I have between fixed data and data that's going to be changing throughout the duration of the application. So here we'll define a public float for the spawn timer. So this spawn timer is going to be continually changing, and so we know when we actually want to spawn on a specific interval. And also we're going to have a public random for, we'll just call it random. We do have a conflict on random because we have two randoms. There is the Unity engine random. However, we actually want to say using random equals unity.mathematics.random. So this is a fully burst compatible random type. And so yeah, let's just go ahead and assign this data on our authoring here. So we'll of course make this a mono behavior, and let's have a couple public fields for the game object, for the enemy prefab, public float for the spawn interval, public float for the spawn distance. And let's also go ahead and define a public unsigned integer for the random seed. Now let's actually go ahead and bake this data here, which we can do a private class baker enemy spawner authoring, and implement that baker there. And of course we need to get a reference to the entity, and we can do our good old get entity. And in here, we can actually use the transform usage flags.none because this is a data only entity. This spawner doesn't need to live anywhere in the world. We're just kind of defining data. And then here we can add whatever components we need to it. So we'll say add component to the entity, and it's going to be a new enemy spawn data. And in here we can go ahead and define the enemy prefab. Set this equal to get entity authoring dot enemy prefab. Again, this is us converting that game object prefab into an entity. And then we need to define the transform usage flags for that enemy prefab. So transform usage flags dot dynamic. Next up, we'll define our spawn interval from the authoring dot spawn interval, and our spawn distance we'll get from the authoring dot spawn distance. We'll also need to add component to this entity of a new enemy spawn state. So this is kind of the more or less changing data. Our spawn timer can just be set to 0 by default, but random, we do want to initialize by using the random.create from index. And here we can just pass in that seed that we are storing in the authoring.random seed. And that is all the data that we need to bake. So it should have everything that we need. And before we forget, we'll just come back to Unity and we'll just add the enemy spawner authoring. And so here we can assign the alien prefab as the enemy prefab. For spawn interval, let's just do 0.5 seconds for now. I'm gonna do a spawn distance of 25, which should put it off of the screen, and a nice elite random seed there. So anyways, let's actually go into, spawning these enemies. So outside of the authoring here, we'll create a public partial struct for the enemy spawn system, which is an iSystem. And so we'll do a public void on update ref system state. So go ahead and create a for each here and do a little placeholder in system API.query. And let's go ahead and look for, we do need to write to that enemy spawn state. So we'll say ref rw enemy spawn state, and we'll also need that enemy spawn data. And once we have those things, we can just say spawn state and spawn data. So the first thing that we're going to do is check to see if it's time to spawn. So what we'll do is we'll say spawn state.value rw.spawn timer, and we'll just subtract this by delta time each frame. So of course we'll need delta time out here. So we can say if spawn state.value ro.spawn timer is greater than 0, meaning there's still time on the timer, go ahead and continue, and then come back next frame, and then once it's finally below 0, let's just go ahead and reset this spawn state timer, and we can get this from the spawn data dot spawn interval. So anyways, once we're past here, we know it's time to spawn. And how do we typically spawn? Well, we like to use good old entity command buffers. So first we'll do an ECB system is equal to system API.get singleton begin initialization entity command buffer system dot singleton. Again, insane name, but again, we want it to spawn at the beginning of the frame, and we'll add that require for update. And let's get a reference to our ECB by doing an ECB system.create command buffer state.world unmanaged. So once we have our entity command buffer, let's go ahead and spawn a new enemy. So we can say ECB.instantiate, passing in the spawn data.enemy prefab. And so once we have that new enemy, we need to figure out a position for it. Again, the way that I like to do this is just kind of like figure out a random angle. And then once we have that random angle, then we'll just take a distance of it. So it's kind of like a polar coordinate if you're familiar. So we'll say var spawn angle is equal to, and of course we want a random angle each time. So again, we're storing random in this spawn state. So we can say spawn state dot value rw. By the way, we do have to actually write back to the random component. Otherwise, the random seed doesn't get updated and we just generate the same random number each time, which is not very random. So anyways, with that random, we can say next float, and then here we can define the minimum and maximum values. So we'll say between 0 and math.tau. By the way, tau, if you're not familiar, is 2 pi. So basically we're finding a radian angle between 0 and 2 pi, which is 2 pi radians is equal to 360 degrees. So we're just, again, finding a random angle on a circle. And then we can create the spawn point by doing a new float 3. And for x, we're going to set this equal to math.sine of the spawn angle. Y is equal to math.cosine of the spawn angle. And then z is equal to 0. You guys are really getting your math lesson here today. So once we kind of have this spawn point, this is really just going to be a spawn point on a unit circle. So now we just need to multiply this by distance. So we'll say spawn point times equals spawn data dot spawn distance. So that's, again, kind of that distance off screen. Now this isn't going to be exactly correct because this spawn point is kind of origin at 0. So we actually want to offset this by the player's position. So we can say spawn point plus equals player position. And we don't have player position, so let's go ahead and get that. You may remember we have done this before. We first need to get the player entity with system API, get singleton entity, player tag, and then we can get the player position from system API.get component, get the local transform off the player entity, and do need to import the local transform. And actually we're just going to get just the float 3 position on there. So then we can, again, add in the position to figure out the spawn point. And then now we just need to apply that to the new enemy. So here we can just say ecb.set component on the new enemy, local transform dot from position, and then just go ahead and pass in that spawn point right there. And then just a little bit of cleanup, we'll make sure that we add in the require for update of player so that, we only run the system when the player actually exists, and go ahead and add the burst compile attribute to the on update there. So now this should spawn these guys off screen and they'll start moving towards the player. So we will go ahead and enter play mode here. And after just a moment, you'll see that these enemies start coming from off screen from all different angles. And again, our attack will always shoot towards the closest enemy to us at any given time. And so yeah, that's exactly what we want to see. We have all these little aliens chasing us and it's a ton of fun. This is what a survivor's game is all about. So actually, let's have when these enemies get destroyed, we'll have them drop a little experience gem for the player to pick up, and then we can increment our little gem counter here. And so anyways, we'll come back to the enemy authoring and we'll create a public struct for the gem prefab. And this, of course, will be an iComponent data. And on here, we're going to store a public entity value here. And then in the enemy authoring, we'll do a public game object for the gem prefab. And then we'll just make sure to add that component here. Add component to the entity, new gem prefab. And for the value, this is equal to get entity authoring dot gem prefab, passing in a transform usage flags dot dynamic, because that's what we want for these guys. So here we're just assigning the gem prefab, and then we can come back to our nifty destroy entity system and then add a nice new little thing in here. So what we can do is we'll say if system API dot has component the gem prefab on that entity, then we'll want to spawn a new one. Now we can spawn them with the end simulation entity command buffer system, but it's not really the best idea because again, we want to spawn these at the beginning of the frame because there's some weird kind of transform issues. So I just go ahead and create a new begin ECB system, and this is system API.get singleton begin initialization entity command buffer system dot singleton. And then the begin ECB is, we get the begin ECB system dot create command buffer state dot world unmanaged, and add the require for updates. So it is up here. So anyways, with this, let's actually get a reference to the gem prefab itself. So we can do a system API.get component of the gem prefab off that entity, and use the begin ECB dot instantiate that gem prefab there. And so actually I need to do a dot value on here so we get the actual underlying type. So anyways, we can say var new gem equals that. Then we do need to figure out where we want to position this in the world. And so we can say var spawn position is equal to system API.get component. We do want the local to world because we want the world position of that current entity that we're destroying. And then lastly, we can do on our begin ECB.set component on that new gem, set this equal to a local transform dot from position, passing in that spawn position. Okay, so let's go ahead and create a new gem prefab. So I'll go ahead and do our good old create 3D quad here, and we can call this the gem. We'll go ahead and remove that collider, and on the mesh renderer, we can set the material to be the gem material right there. And let's go ahead and set a sphere collider on that right there. And we do eventually want this to be a trigger, so we can set that as a trigger. And then lastly, we just need to go to the layer and change that to be a gem layer. So let's save this gem as a prefab here, delete it out of the scene, come back to the alien, and then on the enemy authoring, just drag that gem prefab right in there. So now when we enter play mode, the enemies should start coming towards us, and we can shoot at them, and after a couple hits they will get destroyed and we'll spawn a gem in their place. Now the last thing that we kind of want to do here is pick up this gem and kind of add this to our little experience points right here. So as you can imagine, we're going to be doing a little trigger setup on this gem here. So we'll create one last little script here, and we'll go ahead and do a class, and this can be the gem authoring. And of course, we do need the Unity engine and Unity entities namespaces. And let's go ahead and create a public struct for some gem data. And let's go ahead and create a public struct for the gem tag, which is an iComponent data. Don't need any data on it, but we do still just need to make this a mono behavior. And so we can actually create a private class baker, which is a baker of gem authoring, and then we'll say get this entity with some transform usage flags dot dynamic, and add component gem tag to that entity. Boom. Now also, just kind of thinking ahead a little bit, we do want to eventually destroy this entity after we pick it up. So we can also add the good old destroy entity flag to that entity, and make sure we do a set component enabled on that destroy entity flag for the entity to false. And so here, let's create a public partial struct for the collect gem system, iSystem, and in the public void on update ref system state. We're actually going to need to create a job. So outside of this, public struct collect gem job, which is an iTrigger event job. You need to import the types and implement the missing members, all that exciting stuff that we like to do. And let's get our component lookups. And so also our player is going to need a new data component because we want to keep track the number of gems collected. So we can say public struct gems collected count. This of course is an iComponent data, and then we can say public int value on here, and then we can just add this type to the player just like that. So we'll go ahead and define this new trigger events job. We have a couple component lookups here. A read-only component lookup for the gem tag, so we can figure out which one is the experience gem. The gems collected count is kind of a 2-for-1 here, so this allows us to determine which entity is the player entity. And also in here, we're just gonna directly increment this gems collected count. We're not gonna do any crazy buffering or anything like that. And then finally, we do have a component lookup for the destroy entity flag. And that's because we want to destroy the experience gem when the player picks it up. And then we'll just do our usual determining which one is the gem entity, which one is the player entity. And then after that, we can get the number of gems the player has collected by saying var gems collected is equal to our gems collected lookup at the player entity. And then we can say gems collected plus equals 1. So just add 1 to it. Actually, we do need to do gems collected.value plus equals 1. And then this doesn't actually change the component data for the player. We need to set it back via the component lookup. So we say gems collected lookup at player entity is equal to gems collected. And then finally, we want to destroy the gem entity. So we'll say destroy entity lookup at the gem entity. So we can say destroy entity lookup dot set component enabled on the gem entity equal to true. And that will, of course, just destroy the gem entity. All right, so once we have the collect gem job created, we just need to go ahead and schedule it. Var new collect job is equal to a new collect gem job. Of course, set all of our fun component lookups for the gem lookup. So just go ahead and define the job struct with all the component lookups on it. And then finally, just again, get that simulation singleton from system API get singleton, simulation singleton. And then we can actually schedule a job by passing in that simulation singleton and the state.dependency, and then setting the result of that back to state.dependency. So let's come back over to Unity, and then on our gem prefab, we'll make sure to add the gem authoring component on there. We don't need to set any values or anything on there. And we'll go ahead and enter play mode. And then finally, we can find some of these aliens close by and they'll drop their gems. And we can just go over and collect these. So now we are collecting these gems. And if we just go ahead and pause the game right here, let's find the player and go over to our runtime mode. And if we scroll down, we should be able to see the gems collected count. So we have collected 4 gems. However, we're just not displaying that in the UI right now. We're still showing 0. So the final piece of this puzzle is just going to be to update this UI right here. Now, what we actually want to do is we want to be able to burst compile this collection job. So I'm going to go ahead and just add the burst compile attribute onto that there. And we'd also just, go ahead and burst compile the scheduling of this as well. And the reason that I bring this up specifically is because in the game UI controller, we actually have this public method for the update gems collected text. And all we need to do is just pass in an integer for the gems collected. And because we want this collection job to be burst compiled, because this is, potentially running against a large number of trigger events, we ideally would want this to be burst compiled. This is going to prevent us from directly just calling GameUI controller.instance.update gems collected text with the gems collected value, even though we have the data right there. So what we're actually going to end up having to do is use enableable components to kind of trigger this behavior. So on our player, under the gems collected count, we'll just have a public struct for update gem UI flag, which is an iComponent data, so an iEnableable component. So we'll just add this update gem UI flag to the player, and it can start as enabled. That's totally fine, because we're actually just going to create a new system down here at the bottom. So this is a public partial struct for update gem UI system, and this is an iSystem, and then we'll do our public void on update ref system state, and here we can say for each var in system API.query, and so we're gonna look for everything with the gems collected count, and also we're gonna do that enabled ref RW against that update gem UI flag. And so that way, this gives us access to the current gem count, as well as a flag to should update the UI. So from here, we're not going to burst compile this system. And so we'll say game UI controller dot instance dot update gems collected text, and then in here we can pass in gem count dot value to actually get the value of that. And then we don't want to update the UI every frame, so we can just say should update UI dot value RW equals false. And again, that just disables that component. So now we need to kind of enable this update gem UI flag component. And of course, we can do that from a component lookup here. So I've added a new component lookup for update gem UI flag called the update gem UI lookup. And then we're gonna do update gem UI lookup dot set component enabled on the player entity to true, and then just go to where we're scheduling it, and then we'll add the update gem UI lookup is in system API.get component lookup update gem UI flag, and then we'll just add that component lookup to where we're scheduling the job. So now we'll destroy a couple aliens, and when we pick up a gem, you see that the gem count is now updating. So every time we collect one of these, it's now updating that little UI to display how many gems we've collected. And there are two just other things that I do want to mention. So one of them I think is already implemented. Let me see. If I hit escape, it should pause the game, so I can show you real quickly how this works. And so this gives us the ability to resume or quit to the main menu. You can also just hit escape to re-resume. So just escape to pause, escape to resume. And you will notice that the character animations are all paused as well. So the animations are not playing in the background. So real quickly, I'll show you how to do that. And then after that, I'm very briefly gonna go over how to do the enemy health bar UI. So how the game pausing works is I just already have this in the game UI controller that I shipped with the kind of initial project files. And then, so you just see that right now in on update, I'm just looking for when you press the escape key that we toggle the game pausing and just have this like local is pause variable that I'm just flipping back and forth between true and false. And just setting this pause UI panel to be active, whether it's paused or not. Now, the important part that I want to discuss is the set ECS enabled should enable. What I'm doing here is getting a reference to the ECS world, all from the mono behavior side. And I'm doing that by doing world.default game object injection world. And that gives me the default world. And so first I just want to check to make sure that it's not null. If it's null, we just return out of there because things are going to throw errors. Now, what I'm doing is I'm actually grabbing the initialization system group and the simulation system group. You may remember way back towards the beginning of this video, I was kind of talking about the player loop and how there's kind of different phases of the player loop. And there's the initialization system group, which runs first, and the simulation system group, which runs kind of like in the middle, which is where most of the systems happen. And then finally, there's the presentation system group. So again, all of our game logic is either going to be in the initialization system group or the simulation system group. And that includes all of Unity's game logic for, the transformation system, the physics system, all that stuff. Those are happening just within those two groups. So in order to implement gameplay pausing, what I'm doing is I'm just getting a reference to those top level groups and then just disabling them. And then when you disable them, basically what happens is it just doesn't call the update method for all the methods within that system group. So it effectively just stops the game because the systems are no longer being updated. And so that includes systems like this global time update system, because again, this just runs in the simulation system group. And this is that global time variable that we use to increment the shader property to actually advance the animations. Now, if the system group that this system is running in is disabled, again, this system is not running. So that global time variable is not continually being updated. So it effectively just pauses the animations. So it's kind of a cool little trick that I've been using to implement gameplay pausing and seems to work quite well for me. Okay, and then the final last thing, I promise, is going to be adding in the player health bar so we can kind of see the player's health, have a visual representation of it. So anyways, the way this is going to work is I actually do have this player world UI prefab, and you can see that it's just a regular health bar slider that just goes kind of from 0 to 1 here. And what's going to happen is we're going to spawn this health bar into the world at the start of the game, just under the player here. And then it's going to follow the player around and continually update the health bar to be accurate with the current health value for the player. And then finally, when the player gets destroyed, we also want to destroy the UI element, so it's not just like living in the game world. And so as you can imagine, we need a couple components for this. So we'll do a public struct, and we can call this the player world UI. And this is going to be a special component type called an iCleanup component data. Now with cleanup components, this allows us to do some additional cleanup logic when the main entity is destroyed. So this component gets associated with our player entity. And then when our player entity gets destroyed, when the aliens, attack him, then the player entity no longer exists, except it exists in this little bit of a weird state where it just kind of removes all of its regular components, but all the cleanup components remain on that entity. And the idea here is we can kind of query for that state where we can find something where the cleanup component exists, but some other known components do not exist. And then we can do some additional cleanup logic. And so this is helpful for when we have kind of these linked game objects where we have a game object health bar UI that is going to kind of follow our player around. And then when our player eventually is destroyed, we want to clean up that component so it's not just some like weird empty game object living in the world. And then so on this cleanup component, this is going to be where we have our Unity object ref data to reference the things on the game object side. So we'll do a public Unity object ref. And the first thing that we're going to need is a transform just of the canvas. So we'll say canvas transform. And then we'll also need a public Unity object ref of the slider. And we can just call this health bar slider. We do need to import the Unity engine.ui slider. Now, these cleanup components are a little bit weird because we can't like add them to an entity through baking. So actually we have to do a public struct for player world UI prefab. This can just be a regular iComponent data. And on here, we need a public Unity object ref of type game object. So we're going to be storing a game object prefab for the player world UI, and we can just call this value because there's a single value there. So anyways, come down on the player authoring and we'll create a public game object for the world UI prefab. And down at the bottom of the baker, go ahead and do an add component to the entity. This is a new player world UI prefab. And then the value here is equal to authoring.world UI prefab. And so that's just going to store this Unity object ref inside this player world UI prefab. Now we're going to create a system, and the system has 3 steps to it. So let's go down towards the bottom here and create a new public partial struct called the player world UI system. and this is an iSystem. And in the public void on update, we're going to do 3 separate for each queries. So we'll say for each, little placeholder there in system API dot query. And so we're going to look for that player world UI prefab. And we also want to make sure that we do not already have the player world UI component proper. Now, because we are going to need to add a component to this entity, we also do need with entity access like that. So let's go ahead and name these variables. So we'll say UI prefab and entity. And then to add a component to this entity, we do need to use an entity command buffer. So let's just do a local entity command buffer. So new entity command buffer, and use that state.world update allocator. And then at the bottom later on, we're going to need to do an ECB.playback state.entity manager. Sweet. So let's go ahead and actually instantiate this game object into the world. So we'll say var new world UI is equal to the Unity object dot instantiate, passing in UI prefab dot value, and we kind of have to do the double value because we're saying, you know, dot value for that Unity object ref, and then dot value for the actual, you know, prefab that it's pointing to. So we can just spawn it in the world because it's a full canvas itself. It doesn't need to be parented under anything. And then here we can do an ECB.add component, and we'll add a component to the entity. And this is a new player world UI. And in here, we can set the canvas transform, go to new world UI dot transform. And then for the health bar slider, we can do a new world UI dot get component in children, passing in the slider just like that. And so now this kind of part of the for each loop is only going to run once, basically at the beginning, because we do have this player world UI prefab from the baker, but we don't yet have this player world UI that actually keeps a reference to the transform and the slider. So at this point, we're just kind of adding this to the entity and setting the transform and slider values on that component. And now we'll do another of these for eaches. And this is going to be kind of the for each that updates constantly throughout the application. So we'll do a var placeholder in system API.query, and we are going to need to know the world position of the player. So we can say local to world. We do need this player world UI, which we just added. And then we also need to know the character current hit points and the character max hit points. And so from that, then we can assign some names to these guys. So local to world, we can call this transform. Player world UI, we'll say world UI, current hit points and max hit points. So now what we're going to do is we're first going to update the position of this world UI element. So we'll say world UI dot canvas transform dot value dot position is equal to transform dot position. That's capital P position. So this is setting the position of that canvas UI to the position of the player. And so the canvas is kind of centered on the player, and the health bar, I just kind of manually offset that below center so it'll sit below the player. So now we need to actually update the health bar slider. So let's get the health value, and we can just get this by taking the current hit points dot value and dividing that by the max hit points dot value. So once we have that current health value, we can say world UI dot health bar slider dot value is equal to health value. So a little verbose, I know, but this world UI is kind of the player world UI component. The health bar slider is the Unity object ref. When we do a dot value, we get access to the actual slider element itself. And then the dot lowercase value is us setting the value of that slider. And again, the slider is just from 0 to 1. So it will always, show the correct health here. So at this point, we're instantiating it in the world. We're updating its position. We're updating the slider and all that. And the final step is the cleanup step. So we can say for each var in a system API.query. And here we look for anything that has that player world UI, but has none of the local to world. So basically, if the local to world does not exist, then we know the entity has been destroyed, but that cleanup component still needs to be cleaned up. And we do need entity access here as well. So let's set these names for world UI and entity. And so first I always check to see if the world UI still exists. So we can say world UI.canvas transform value is not equal to null. Then in that case, we'll say object.destroy, passing in the world UI.canvas transform.value.gameObject. Like a little bit of a roundabout way of getting to it, but again, we got to go through this Unity object ref, do the dot value, which gets us the transform, and then from the transform, we get reference to the game object, and we're actually destroying the game object. And then, so anyways, we can do an ECB.remove component, and we want to remove that player world UI from the entity. And again, this is a cleanup component, so we need to specifically manually remove that component in order for that entity to get fully destroyed. So anyways, that is the player world UI system. We cannot burst compile it because we are using managed types here. So let's select the player and go to authoring mode. And on the player authoring, we just need to set the player world UI prefab like that. And now when we enter play mode, you'll see that the slider is now following the player. And then if we do get damaged by any of these entities, you'll see that the health bar goes down, and it's going to stay at that level. And let's see if we can actually get the enemies to destroy us here. And then boom, once it reaches 0, we go into this game over state. And yeah, so that is kind of a little survivors game made with Unity ECS. Really hope you enjoyed this tutorial. And so actually, I'm not going to leave you on that. I'm going to leave you with a challenge. The challenge that I have for you is that you'll see over in the materials, we do have a Reaper alien material with this awesome Reaper, again, created by Sil over at Penzilla Design. And what I would like you to do is to create a Reaper prefab that will actually spawn into the world after some set duration of time. And this Reaper should deal enough damage to the player to destroy it immediately. And this Reaper should also have enough health where the player can do nothing about it. So you should have everything you need to know to implement this Reaper alien. Again, the final project files will include kind of one implementation of how to implement that. And another cool thing that I would try and challenge you to have to do is when the Reaper actually gets spawned, that you should destroy all the other existing aliens and make sure no subsequent aliens spawn after that. So anyways, I'll leave you with that and do a little outro here for you in just a sec. So anyways, that's how you can create a simple little survivors type game using Unity's data-oriented technology stack and their entity component system. Really do hope that you learned a lot in this video, and I'd really do again encourage you to try out some of those challenges that I pitched out to you throughout this course of this video. And also feel free to just go in and start playing around with things, crank up the numbers really high and see where things go. You might be surprised at some of the numbers that you can achieve on your machine. And then just wanted to remind you one last time that this tutorial is again just kind of the introduction into dots and ECS, and if you do want to take it a step further, go check out the product that I have over on the Unity Asset Store, where I have all the project files for my shipped Steam game Dot Survivors, as well as a whole bunch of documentation, both written and video, detailing all of the most important concepts of this game. and how everything all fits together. There is a ton of great information in that product, and I'm extremely proud of it, and I really hope that you do learn a ton from it. So anyways, thanks so much for watching this tutorial. I really can't wait to see all the amazing things that you create with dots in ECS.